Okay, good morning. So what we will do is today in this talk we will discuss about the power electronic converters which are usually employed in connecting renewable energy sources, and I will mainly discuss the utility scale. I mean, large power, more than a megawatt, in that scale, large solar park or wind generators, not the rooftop solar. And I'll skip this. So I will briefly introduce our lab. So we call it Sustainable Power Electronics Lab. It's called SPEL. And currently I have about 7 PhD students, 3 MTech and 2 project associates. Mostly our research is funded by Government of India, MIT and DST, ANRF. And 70% of the funding comes from government and the rest comes from the industry. We work with a lot of industry, the bigger ones like TI, Delta, and then startups like Arbor Mobility, and mid-sized companies like Ethar and all. And somehow after COVID, we got a lot of support from industry, and industry is more active and we are able to do a lot of work with them. So we work on converters from few kilowatt to few hundreds of kilowatt, and for various different applications, from server power supply to your laptop charger type of thing, to medium power like 10, 20, 50 kilowatt, which is for charging of traction motors, driving traction motor and charging of electric vehicle charging. And then high power, where we connect with the solar and wind to the grid, right? So the full spectrum we work. And one thing that we try to focus is that whatever research we do, then we try to convert it to transferable technology. And students are also very much encouraged to develop converters which are quite cutting edge and can be worked into a product. So today the talk that I am going to tell you about little bit of research and this in this area was actually done by 3 of my students. Anirban has graduated some time back and currently he is working with GE, and Hari and Surjo are currently they are my students. So Hari is a very bright student from Kerala. He is from NIT Calicut, and I am blessed to have very good students. And whatever I am going to present, it is basically their work, not mine. I am just there. So if you look at utility scale solar, so where we are talking about more than a megawatt, right? So they are called, so actually the solar, the power is available from the solar field as DC, correct? And if you look at for a particular irradiation or sunshine, the power available is a function of the terminal voltage. So you can see that there is that is the curve that's there, right? And so you can see that there is a point, if you keep the voltage at the terminal, control it to this voltage, then you can extract the maximum amount of power, and this point is called maximum power point, right? So now what happens is that to connect this DC voltage to the grid is 50 Hertz grid, right? To the grid, what you do is you use a DC to AC converter, correct? It's basically an inverter or a rectifier, whatever way you say it. So what happens is that this DC to AC converter actually controls the voltage here. It's a grid tie inverter, we call it. it controls the voltage, this DC voltage to this point, right? Regulates it to this point so that you can extract maximum amount of power available and push that into the grid. And so it takes the DC and then converts into a 50 Hertz AC. Now what happened today is, usually the solar fields today in India, if you look at, they are of 10 megawatt onwards, quite big. The Pavagoda, I think it is more than 100 megawatt, and one of the largest solar field in the world, right? It is in Karnataka. And so today what happens is that this voltage at the terminal, right? So lot of small solar cells are basically connected in series parallel combination to get you this voltage. So even though the solar parks typically are of tens of megawatt, but one unit of inverter, today we cannot build a 10 megawatt inverter till today. We will slowly, things are improving and things are increasing. Say for example, at the beginning of 2010, the inverters used to be 350 kilowatt, one inverter, and then you will parallel multiple of them on the AC side. Then slowly the power started increasing, and towards the end of last decade it was about half a megawatt, and this voltage used to be around 800 volt. So you can use 1200 volt IGBT in the two-level architecture, 3 legs with two switches in each leg, right? The regular inverter, and connect it to the grid. That was the technology till 2019, 2020. But we always, for high power, we always want to put more voltage so that the current is low, the losses are low. Correct? That is the regular business that we try to do. So today, typically, a lot of manufacturers have pushed the inverter rating, unit inverter rating, to about 1.2 to 1.5 megawatt. And the voltage here has risen to about 1200 to 1300 volt, around that range. And what people are doing is, you take 1200 volt IGBT but put it in a 3-level configuration so that it can block 1200 volt DC bus, right? So that is what currently, if you look at the market, that is what is now the trend. But there are a lot of 2-level inverters are still in use. They use basically IGBT technology. The switching frequency will be somewhere around 10 kilohertz, 5 to 10 kilohertz around, and the power is half a megawatt to 1.2 megawatt. But when you go to 1.2 megawatt, it is 3-level inverter, not 2-level inverter. So that is what is happening. And they call this central inverters. You must have heard the term string inverter and other, but for large parks, it is the central inverter architecture. So you combine and make one central inverter, and of course for tens of megawatt, there will be 20, 30, hundreds of such inverters connected on the AC grid in parallel. Now what happens is that when you connect this, right, the power actually is in megawatt, right? So what people do is, you will have a collection grid in the park. So the collection grid is typically 11 kV to 33 kV in India, right? So so at the output voltage of each inverter is still today about 400 volt, our regular low voltage AC. So just at the inverter, you are going to have one 50 hertz transformer that will step it up to 11 kV, right, or 33 kV. And then in each unit of half a megawatt to 1.2 megawatt. And then you will be connecting them to the collection grid, what we call that 11 kV or 33 kV collection grid. And then the park itself will have a big step up power transformer that will step it up to higher voltage like 222 kV or 400 kV or something like that, when the power is in hundreds of megawatt, when you have collected all of them, right? And then it goes to the transmission network. They do not connect this in the distribution grid. typically what I am talking about today. See, rooftop solar is different, that you connect to your distribution grid from where you are taking power for your home, right? The same place. So we are going to talk about this thing. So these are called central inverter. There are many players in the field. Of course, China dominates, and you have, of course, ABB, like one inverter that you see. This is a 2 megawatt unit, but inside there will be, I think, 4 inverters are there inside, connected in parallel. So now let's look at the utility scale wind. What is happening with the wind, or how you do it. So in wind also the graph is similar as you have seen for the solar, but in wind what happens, the power that is available at a particular wind speed is actually a function of the turbine speed, right? And you see the similar graph is there. So what you will try to do is, you try to control the speed of the turbine at this particular speed, right? And by controlling the generator speed by using a AC/DC converter, right? So this is what you do, and try to extract the maximum power. By the way, I should tell you this. There is this is also a little bit confusing. See, the thing is that when you are extracting maybe 10 kilowatt, 100 kilowatt, you can simply push it to the grid. But when you are generating in megawatt level in a transmission system, you cannot just simply push, close your eyes and push power as much you are generating. Because now you have to have the power, like our synchronous generators, which are operate in hundreds of megawatt. You need to look at the frequency and then push the power, like what happens in synchronous generators. So it is not true that for high power inverters that we always operate at this MPPT point. Of course, we cannot go beyond this point, but typically what will happen is there will be a governor, like frequency controller will be there. That frequency controller will tell you how much power to push, where the default setting will be whatever the power that the utility has promised to supply, right? So the thing is that many times, or most of the time today, we don't operate at this point. We will be operating some point like here. Okay, this is very important, and that is called the cuddle point. Say for example here the power available is 800 kilowatt, but actually you may be, and that this voltage is let us say the MPPT voltage at this point is 800 volt, right? But you will be operating somewhere here where actually you are actually pushing 500 kilowatt, and the voltage is maybe 1000 volt at that point, right? The interesting thing is you don't operate here. Why you don't operate here? Since the same power is available at 2 voltage, because at lower voltage current will be higher, so it will be more lossy. So you always want to operate from this point to this point, or control your voltage between these 2 points, right? So same thing is true with wind also. So it is not true that we always extract the maximum amount of power that is available for that wind speed by controlling the permanent magnet synchronous generator speed that is connected to the turbine, right? But so, and what happens here? What happens here is that you have see here what I have drawn is a permanent magnet synchronous generator. This is called a direct drive type of this thing. So what happens here? Simply you have one AC to DC converter. This is called, people call it, generator side converter, GSC. And with that, you do vector control and try to control the speed to this point so that you can extract maximum power. And the voltage that is generated here from at the terminals of the synchronous generator is an AC, 3-phase balanced AC. But it is a variable frequency, so we cannot connect it to the grid. So what we do is we use a back-to-back configuration. So first you have the generator side converter, which will be doing the vector control to control the speed of the generator or the turbine, and then you have and rectify it to intermediate voltage here, and then from that intermediate voltage you will use another DC to AC converter. That converter will convert it to a fixed frequency 400 volt 50 hertz AC, right? So that is how the how these things are, let me see, that is how these things are done today. See here also the same story. Now today one wind generator sort of can go up to 3.3 megawatt it can do, right? One tower can do, and then you have, but the thing is that the power is generated again at low voltage, because the generator voltage is around 500 to 600 volt, around that, right? So what you here rectify it to 800 volt to, you know, it could be up to 1.2 to 2 kV, right? And again here what we do, we use IGBT and we use multi-level configuration with 1.7 kV devices. People also use 3.3 kV IGBT in this kind of configuration. Switching frequency will be somewhere around 5 kilohertz. See, what I am doing is I am spending more time telling you what happens today rather than our, you know, complicated research, because this is what is more interesting, I think, and you would like to know what is happening today and where is the trend and all of that. So here there is one very interesting problem is there. Okay, by the way, so you convert it to fixed frequency AC, and then you know you have a step up transformer. With that you connect to collection grid. Here collection grid can go up to 66 kV, and then there will be a step up transformer in the the wind park that will take it to 400 kV on things like that and connect it to the transmission network. Right? That is how it is done. So this I have drawn from PMSG. This is the current trend, but till today, I would say 80% of the industry use doubly fed induction generator. That you know that converter rating is lower, but the flip side of that is, see, I have not drawn that picture here. The flip side of that is that you know the machine is more exposed to the grid, so any grid fluctuation will impact your generation. So that's so you see that here also you have ABB and many other companies are there. Howie and all they make these converters, and typically, as you can see, I told you few megawatt it will be. So now this is the today story, right? And what is some of the problems of this, right? So one of the thing is that you know to connect to the collection grid, you need to actually connect it through a low frequency 50 hertz transformer. This transformer is actually 50 hertz, so it is large. So the frequency of the transformer is inversely proportional to the size of the transformer. So it's a 50 hertz transformer, and so the thing is that the entire megawatt, like you know, you are maybe each of them is 500 kilowatt, but the entire 100 megawatt power, say in Pavagoda, has to flow through that much of iron and copper, operating at low voltage AC 50 hertz, right? So this is actually a huge material footprint, right? And as you know that the copper, probably will start investing in copper sometime soon, because copper is becoming very expensive, right? So that's a flip side, and I will tell you, I have worked in this industry. The transformer cost is almost 50% of the inverter and other electronics cost, right? So it is expensive also. It's not that it is cheap. And in wind, something very interesting happens. So the wind, usually you have seen that the tower is there. Usually that is like 80 to 100 meter. Now people are trying to push it even further. So 80 to 100 meter tall tower is there, and on the top you must have seen that is called a nacelle. inside the nacelle you have the generator, which is connected to the turbine. Turbine is with these 3 blades are there. So now that generator voltage, output voltage is low voltage AC. It is 500, 600 volt, right? So now, and then you have to connect the AC DC and DC AC, right? To connect it to the collection grid through the transformer, right? Because it's a low voltage. But the thing is that the nacelle, the space is not enough to put the transformer and all the electronics, right? Now the electronics can be put, no problem, but this transformer is very heavy, right? It cannot be put in the top of the tower. So what happens is, now the cables come from the top of the tower, which is generating at variable frequency AC, low voltage AC, and the entire power is coming down. So the currents are pretty high, and you use very thick copper. That's quite a lot of expense in the in this entire electrical system, and also loss, right? And you see, again, the thing is that each unit may be 1 or 2 megawatt, but finally that 100 megawatt, all of that is going through that only and experiencing that same amount of efficiency drop in the process. And one estimation says that about 3 to 5% is lost in that. That's a lot of power, a lot of energy that is being actually lost. So, and you will see that at the bottom of the tower, usually there will be a green color box will be there. That box has that AC, DC, DC, AC and the transformer in it. So this sort of sets the stage of, see, this is what is happening today, right? I tried to give you a picture of this, and then I will tell you what we would like to see happen in future, right? So you see, in both of this problem, the thing is that we are using a low frequency transformer, 50 Hertz transformer, which has a huge material footprint. It adds to the cost of the electrical system. And also the thing is, for wind, because of this, we have a huge power loss happening in the system. So what can be done? See, in this wind problem, if the transformer is light and small, I can put it to the nacelle, right? No problem, right? So how to reduce the size of the transformer? So to reduce the size of the transformer, what you have to do essentially is increase the frequency. That is all about power electronics. Higher the frequency, smaller the size of the passives, right? That is what it is, business is. So the thing is that instead of 50 Hertz, if I can do this stepped up, right, at low voltage, at high frequency, then the size will reduce. And that is what is the following the trend of power electronics. I mean, that is what we have done so far, right? So now the thing is that you can do that, but what are the challenges, right? So now you see that if you look at the standard system, right now what we just talked about, that you have DC to AC, and then you have a low frequency transformer connecting it to the grid, right? So now the thing is that this DC to AC, this side you take 800 volt, okay, standard. This side you take 400 volt. It will generate 400 volt or 415 volt, 50 Hertz, a 3-phase balanced AC, right? And if you take half a megawatt, with today's, I think 6th generation IGBT, today it is going, with today's technology at 5 kilohertz to 10 kilohertz switching frequency, the efficiency of the DC-AC bridge here, along with the filter inductor, there will be an LC filter there, is close to more than 98%. More than 98%, right? So typically the loss in the bridge is in the order of 1%, and loss in the LC filter is about another 1%, so 98%. And this low frequency transformer, see, we have worked on this low frequency transformer for last 100 years. So it is very good. So that peak efficiency at the peak power, it can be optimized to 99%. Right? So then if it is 99%, this is 98%, the overall efficiency of this system is about 97%. But of course, in wind there is a connection here. That connection before this, where the loss is happening. So I'm not talking about that. See, both for the wind and solar, you have this DC-AC and transformer to the grid, right? All of us can see that, right? I'm just talking about that part of the system. So now the thing is that here is a picture. That picture shows that there is a 60 Hz 100 kV transformer, and here is a similar, I think this is 140 kV 20 kilohertz, but the power is same here, right? But the frequency here is much higher, right? And you see the size is reduced almost 10 times, correct? So that's basically what happens. But this is also not that simple. The physics is not that simple, because what happens is that the losses will be there, and if you go high frequency, there is also a transformer. Inside the transformer there is hysteresis, right? Hysteresis loss and eddy current loss is proportional to frequency and frequency square, right? So their loss is going to increase. And also, because the size is now becoming smaller, if your loss increases, dissipating the heat is not that easy, because dissipation of the heat or how you extract the heat depends upon the effective area available, right? So that's a challenge in the transformer design. And the thing is that our usual wisdom of building 50 Hz transformer is not same as building this kind of transformer, which is doing megawatt, doing at 11 kV on that side, and also doing it at say 20 to 50 kilohertz, not 50 Hz, right? So technology requires this thing. But the bigger problem is, even if I say that the frequency of the transformer, the efficiency transformer, I can make it high, let's say. The bigger problem is that, see, here the efficiency of the standard system today is about 97%, right? But how will you get high frequency? So now to get high frequency, what you do is, this is the standard power electronics approach. What you will do is, you are going DC to AC. So you are going to have an isolated DC-DC converter, a DC to DC converter, which incorporates a high frequency transformer. We will take a closer look to that, right? And then followed by a DC-AC. Now there is no transformer here. You can directly connect it to the grid. Now this DC-AC converter will remain as 98%, which was there before. The transformer is missing here, correct? But I have to put this DC-DC converter. And inside the DC-DC converter, actually there is a low voltage DC to, you are going to convert it to high frequency AC, and that high frequency AC will be back converted to DC. So there are two stages will be there. I think if you have some background in power electronics, this is like the phase shifted full bridge converter we use. DC to high frequency AC to rectify it to DC. But there are two stages of power conversion. So the thing is that usually the DC-DC converter, at this power if you build, efficiency will be above 90 to 93%. Maximum if you use silicon carbide and all those things, then it can move to about 95%. 97% is quite, it is difficult to achieve that, right? So the thing is that overall system efficiency will be close to 90%. So that is why, even though this idea is there for a long time that you can use power electronics and replace that low frequency transformer, till today there are no product which does this. And this concept is called solid state transformer. Probably you have heard of it, right? Solid state transformer. So what is the time? How much? I have another 20 minutes. So the thing is, what I have done today till now is, I have told you what happens today in utility scale generation with renewables, and where is the trend going, I told you, and also I told you some critical issues and the problems with it. So now I am going to give you a brief overview of some of the work that we are doing with respect to this. And I am not going to go through some of the complex slides here, right? Because I think many of you may not have a, that kind of background in power electronics. But I hope you overall understood where we are today and what is sort of the problems are there, right? So another place also where this kind of systems are there is fuel cell, right? So in fuel cell, what happens is that you basically in the fuel cell the input is hydrogen, right, and oxygen. You take hydrogen and oxygen, combine them together, make water, and generate electricity. That is the business. So here energy is stored in the form of hydrogen essentially. Hydrogen is the storage, and in many applications like say in the server power supplies and that kind of thing, where data centers, right, where the fluctuation is power is dangerous, because see all your SBI account information is there in online. If you suddenly try to log in and see nothing is coming there, we are in big trouble, right? We will not sleep. So power in the data centers cannot be interrupted. In some of those kind of data centers where all your banking information is there and critical security related information is there, there cannot be load shedding there, right? And many of these data centers, that is why they are backed up or they use fuel cell, because fuel cell gives you a steady power supply to the data center, right? So that is one of the reasons where critical data centers, see if Facebook can go down, that's fine, but banking system cannot go down. So that's why the fuel cell is that is one of the big application of fuel cell in grid kind of support, right? The fuel cell also has this. So you have each fuel cell will be somewhere around 30 volt, and then you have an isolated DC-DC converter, and then you have a DC to AC, and then you connect it to the grid. So I will just give you see, this is the picture I was talking about. So what happens here is, see, this is a edge bridge rectifier, right? It takes DC and then it chops that DC here so that there is an average AC in there, right? So that it makes from DC to AC, basically, that is what happens. And in isolated DC-DC, what happens is, you take the DC, maybe this is the solar output, and you use an edge bridge at high frequency to generate a high frequency square wave AC, correct, like this, quasi square wave AC, okay, and then you pass it through the transformer. This will be 20 kilohertz to 50 kilohertz, that is what I am talking about. And then there is a rectifier which will rectify this to a DC back, and then you put an LC filter, you get the DC, right? That is the whole idea. So the thing is that instead of connecting just this inverter with a transformer to the grid, now what I am doing is I am connecting this DC to the grid using a isolated DC-DC converter. Isolated means which incorporates a high frequency transformer, and that is my transformer here, correct? That is my transformer here. It is operating at high frequency, so the size will be smaller. But you see, I have so many power conversion stages that makes life very difficult. Like, so the efficiency will be poor here, right? And efficiency is a big deal, because in megawatts, right, if you lose 2, 4, 5%, or what I'm saying is that with current technology, efficiency of this system, if you compare with this inverter with just a low frequency transformer, that is 97%, but this will be close to 90%, right? Not good. So here what happens is that there is I think I cannot okay, I'll tell you the big picture, right, of this. So this is the status. So now how we can solve this problem, right? How can we make this system 97%? That is basically the question, right? How can we do that, right? That is the research. So now the thing is that if you look at, then we need to, so what is the problem we are targeting here? The problem is, okay, with this I can achieve a high frequency transformer which will have a very small footprint, and it will solve my problem that I have discussed so far. But what is the other side? Other side is the efficiency is poor. So now where this efficiency is going, where the losses are happening. Now in a power electronic converter, the heart of the business are semiconductor devices or the MOSFETs or the transistors. And here, like digital electronics, we operate them as switches, electric switches. So when the switch is on, it is a short circuit, voltage is zero and it takes current, and when the switch is off, it blocks voltage, current is zero. So what is the loss across a switch? It is voltage into current, correct? That is the loss across the switch. So for an ideal switch, in the on state voltage is zero and in the off state current is zero. So for an ideal switch, loss should be zero. But we all know that switch is not ideal. So when the switch is conducting, the voltage is not exactly zero. There is a drop, and that is called conduction loss. That results in conduction loss. And when the switch makes a transition from on to off or off to on, the current will say, for example, it is turning on. So the current has to go from zero off state to some value that is going to carry, and the voltage has to go from non-zero value to zero, right? So now during that time, I may have a figure here. See this I am talking about, right? This is a switch turning off, right? So now during this transition, there is an overlap in the voltage and current waveform, because they don't change ideally at 0, like that, right? And because of that, no, there is a blip in the VI product. So this much, so the energy, the area under this, this triangle is what you are losing every time you are switching. So this energy multiplied by the switching frequency, that means how many times you are making that transition per second, correct? Per second, that is multiplying it by frequency, is what is your loss. Loss is energy lost per second, correct? So now if I increase the frequency to reduce the size of my transformer, the loss in the switches, or what is called the switching loss, is going to increase, right? And that is where I am unable to increase it or get to the solution. So how can I overcome this problem? There are two ways to overcome this problem. One is that you use a switch that is faster, right? So where this overlaps, you can see the current from where it is coming down and the voltage to where it is going is decided by the circuit, 800 volt, 300 ampere or whatever, right? That is same whether you use IGBT or whatever, right? But the thing is that the time it takes is actually depends upon the technology of the switch. Now the IGBT switch is slow, right? But if you use silicon carbide there, which is a new technology, which has come up in last 10 years, right? There, so IGBT in this kind of converter usually takes about 1000 nanosecond, close to a microsecond to switch. But silicon carbide for the same rating can switch in below 100 nanosecond. So there is a 10 times smaller. So obviously then this lost energy will be small, 10 times smaller. So you can push the frequency for the same loss now 10 times more, right? So that is one way to proceed towards it, and this is what people are doing. And the other side, how can you do that, is what we call soft switching. If you are from power electronics, you may heard of this. So in soft switching, what happens? No, when the switch turns off, we don't let the voltage go that fast. We keep the voltage low till the current has fallen to zero, right? How we do that, I cannot explain. That's a power electronics class, right? But this is a trick that is being done during turn off, and we try to use this trick so that all of our transition is actually a turn off. Turn on happens in little different way that I am not discussing. so that I can avoid the switching loss, right? So there are two ways to circumvent this problem. One is use better switches, silicon carbide and all that, and another is try to use this soft switching transition. Now switching transition, making it soft for all switching transition is a very challenging thing, and that is what the research is about, right? So now I told you little bit of towards the solution people are thinking and doing, right? So I will skip through all that, and I will, let me see if I have a picture. So let me tell you another interesting application of this. So more or less, you know, what I wanted to tell you in this talk I have told you. So I'll just summarize quickly in 30 seconds. Today, how the utility scale solar and wind is connected to the grid, I told you, and also I told you how the trend is, and I told you what are the major problems in that, and I told you where the research is and how to sort of solve that problem. So now the thing is, so we work in this area, right? So and try to solve the problem using silicon carbide and, you know, soft switching techniques. So we basically, you know, try to come up with new topology, or which is the converter architecture, and we come up with a switching strategy, that is what we call modulation strategy, where almost all the switching transitions are soft or lossless, right? So that switching frequency can be increased. That is basically what we are trying to do. And you know, here is a solution. I know it is quite complicated to see this, right? So here is the PV source and here is the grid, right? Now because the grid is at 11 kV, and today the devices that we have that can switch faster, silicon carbide devices that can switch faster, they can block only 1200 volt. But you know, the AC that you are getting connecting, that AC is not at 400 volt, no. You have to step up and connect to 11 kV. So I cannot just simply connect a 2-level inverter there, like I was doing in case of low voltage AC, and then you have the step up transformer, right? So you have to use some kind of a series connection that is called multi-level inverter connection. So you can see here what we are doing is essentially, let me see if I have a better picture. Okay, don't worry about it, I will explain it to you. So here is 11 kV, and then if you look at, these are three phases A, B, C. So then each phase, now if you look at this red box, right, there is an edge bridge here, 1, 2, 3, 4, maybe a multiple. If it is 11 kV and if you have to have 800 volt, then I think you will need about 12 edge bridges to be connected. So each edge bridge is making one single phase AC, which is about 400 volt, and then you are series connecting them, you see, to get to 11 kV, correct? Actually this is the line to neutral. Line to neutral will be lower. 11 kV is line to line voltage, so 11 kV by root 3 into root 2 is the peak that you are going to actually have to block. And then what we do is we make, so with that we make the AC, and here you have the DCs, and this is actually a DC to DC converter. So I will not go into this, this is little bit complicated, but this thing, no, that if you just look at this, what is happening, one side you have a low voltage DC, another side you have a medium voltage AC, 11 kV, 50 hertz, balanced 3-phase AC, right? And we have galvanic isolation in the converter, and that those transformers, these are those transformers which are operated at 20 to 50 kilohertz, correct? So I don't have any low frequency transformer here, and the medium voltage AC and this DC are galvanically isolated, and also the step up is achieved. But of course I need lot more devices here processing that amount of power. So this is what is called, you know, solid state transformer. You will hear that. Some people also call it power electronics transformer. That is an upcoming technology. Not there in the market yet. But I believe it will be there in next 5 years. And it will change the scenario, how things are done. Now, what we are doing in the lab, right? So now I do not have this picture. Somehow I should have put that picture. I will explain. I will tell you. I think you understood. So, see, we are actually building a solid state transformer in the lab, right, with Delta Electronics, where the solid state transformer, we will connect it to 11 kV on one side, and we will have two DC ports, which is 800 volt and 400 volt. One of them will be 200 kilowatt. Actually here it is not written correctly. This also will be 200 kilowatt. See, this is the low voltage DC. This is the low voltage DC. This is the medium voltage AC. So this is a medium voltage AC to LVDC converter, which incorporates galvanic isolation at high frequency of 20 to 50 kilohertz. So this is actually a solid state transformer, this green box. And this we are developing in the lab is, this is a half, you can see this is a half a megawatt system. Correct? It's a half a megawatt system connecting to 11 kV. Now, till now, only Delta Electronics US has a prototype in their lab which connects to 13.8 kV, it is in US 60 Hertz, 13.8 kV 60 Hertz to an 800 volt DC with high frequency isolation, and power rating there is about 400 kilowatt, right? So now if we build this, this will be the second one in the world of high power, and with this, and their overall efficiency is about 95% that they have been able to achieve. And our target here is to achieve something like 97% from LVDC to MVAC. So that's what we are doing. So, but we are doing this for electric vehicle charging application. I will just take 1 minute to tell you that application. So I think I have 1 minute. I'll just tell you in 1 minute that application. See, in four-wheelers, right, the battery that is there, which is the fuel tank, is about 50 kilowatt hour. That can take you in one charge to 300 kilometer, like your petrol in petrol vehicle. Now the batteries can be charged today maximum at a rate of 1C. That means the 50 kilowatt hour amount of energy that you can pump into at 50 kilowatt rate. So how much time it will take? Approximately 1 hour. 50 kilowatt into 1 hour is 50 kilowatt hour. If you charge at half a C, that is 25 kilowatt. So it will take how much time? 2 hours, right? So now charging 1 hour is too much, right? Usually when you are filling the gasoline, it takes about 2 to 3 minutes, the petrol. And you know what is the power there? More than a megawatt. Actually, the way you are transferring, you are just mechanically putting this liter, but it is about more than a megawatt. Actually, you are transferring there, right? So now the battery technology is improving, and you already know that this Tesla superchargers are there, which is this like 250 kilowatt. So now, if you think 200 kilowatt, it is going to go soon from 50 kilowatt. So today on your highways, the chargers that you see, say from ABB, Delta, those are 50 kilowatt charger approximately. It takes 1 hour. So you have your coffee, go around, do this and all that. Takes too much time. But it is soon going to become 200 kilowatt. 4 times. So it will be like 15 minutes it will become. Now, how much is the power that we usually consume at our home? About a kilowatt maximum when your fridge is running, your washing machine is running, everything is running. So 200 kilowatt is 200 houses, it's like a village power or a big apartment complex power, right? So if you are charging 3 or 4 cars, it is about 1 megawatt power. So 1 megawatt on a distribution grid cannot come at 400 volt. It will come at 11 kV. So today how people are doing, again 11 kV is coming, you have a step down transformer to 400 volt, and then you have a DC 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 AC, right? That is how it is done, right? If all these chargers that you see on the roadside are like that, but you have this large low frequency step down transformer is there. So again the problem is same. I am going to a DC to the battery, and the car batteries today is about 400 volt, and it is increasing, and within 1 or 2 years it will become 800 volt standard. So 800 volt on the battery side, isolation other side is medium voltage AC 11 kV. So the problem is same what we discussed with the utility, integration of wind and solar, but only difference was their power was flowing from DC to grid, and here the power is flowing from grid to DC. That's all is the difference. And tomorrow if you want, because these are going to be big power sources, the batteries, so if you want some grid support, people are talking about vehicle to grid, right? So you will be also doing some frequency support if required, if lot of batteries are connected, or say for example if there is a contingency, say some flood happens or something happens and load shedding, the actual grid is not available, but you have those batteries inside your car, with that you can lit up the town, right? So that is V2G, whatever, vehicle to grid. So these converters can be bidirectional between DC AC, low voltage DC to medium voltage AC. So this is what we are actually doing in the lab. So you see this is the structure of this. So these two, the load is actually 2 car emulator. Okay, so these are basically, they are like car battery. They will behave like car battery with a dispenser and gun. And in the lab at ISC we cannot draw half a megawatt, right? So what we do is we actually circulate the power. We circulate the power, right? So in the lab we have a 400 volt 50 hertz grid. So then we take that and then we step it up to 11 kV, connect it to our converter, and then we push the power into the battery emulator, and then the battery emulator on the other side is connected here. So the power is actually flows like that, and from the lab grid you only take the losses, right? So this is something that we are doing, right? And which is related to solid state transformer, but only thing is what we have discussed before is power is flowing here on the other way, from MBAC to DC, and not DC to MBAC. Right. So I think I am going to, how much time I have? Maybe, 5 minutes more. So another interesting project maybe I will tell you is, so see in India two-wheelers are big, right? So two-wheelers, actually if you look at the battery of the two-wheeler, it is about 3 kilowatt hour, and with 3 kilowatt hour battery you can go about 90 kilometers, which is same as if you put petrol in your regular two-wheeler, right, a scooty. So but of course it depends upon how the hilly area and all of those things, but approximately that is the thing. And if you see today, all this Ola, Ether, these people give you a 700 watt portable charger. That portable charger is about this size, okay, 3 liter in size. How is 3 liter? 3 liter is Coca-Cola bottle, 3 liter, right, big bottle. 3 liter in size, about 3 kgs, 2 to 3 kgs. So is this portable, that big Pepsi bottle? It is not portable. It is quite heavy, right? Not like your laptop charger that now you can put it in your pocket, right? Or the phone charger. That is portable. And that takes about, so if it is a 700 watt charger and you have a 3 kilowatt hour. So how much time it will take approximately? 3 to 4 hours it will take, right? And then you have these fast chargers which are there in the EV stations, which are about 3 kilowatt, 3.3 kilowatt. With a 15 ampere socket you can take 3.3 kilowatt. So 3.3 kilowatt, 3 kilowatt, 1C charging, 1 hour. But if you are going by two-wheeler, suddenly you want to charge, you will stand somewhere for 1 hour. First you have to find out where it is and then stand, very inconvenient, right? So the thing is that how can I actually make that, and these 3 kilowatt chargers are big, they are wall mounted. I think some of them are here in the display, right? They are big and wall mounted, right? So the question is, to make really this thing happen, you need to have a charger which is like this, like your less than 1 liter bottle, Pepsi bottle, right? That should be a 3 kilowatt charger, and also that should not get very hot, right? It should be air cooled, right? So the efficiency also has to be higher, not small. So what we have done is, again, the size business in power electronics is inversely proportional to the frequency. So you increase the frequency, it will reduce. So we used here gallium nitride because it's a low voltage, not silicon carbide. So gallium nitride based. So we have made a charger with CDAC Trivandrum was our partner in that. So with their help, this was a project that we worked on. We developed a charger where the power density, this is a 3 kilowatt charger, and the size is like this. Maybe 3 or 4 of your phones, if you put, it will be like that. It is that small. And so this more than what we say 40 watt per inch cube, the density. It is one of the highest power density converter that is available if you take all the products or what is reported in the literature. So right now we have a startup that we are transferring the technology to them. A student is doing that. So I think I will stop here, and any questions or anything that you may have. Thank you.
Any questions? Sir, in the power Goda 100 megawatt in solar power field in Karnataka, so the inverters are arranged in tandem or like that. So the cooling, how the cooling arrangement is being considered?
Sir, the thing is that I do not know exact power rating there, but I assume it will be somewhere with central inverters are there, half a megawatt, like I said, right? And they are all parallel on this side. And in my understanding, because the size is not really a big problem there, most of the solar inverters are air cooled. They are not water cooled, because you can have a bigger inverter there, no problem. Solar fields are anyway that big. So the thing is, they are all air cooled, sir. And the efficiency is high. They operate around 98% or above. So the losses are only 2% loss that you have to manage.
Yes, sir. As you told that the switching devices like say MOSFET or other things by carbon. Or like. So the speed goes, the harmonic levels about the harmonic, then filtering design. Is it changes?
So sir, what happens is that say if you are making 50 hertz AC, 5 kilohertz switching is fine to give you a good nice sinusoid there, right? But the size of the filter, that LC filter that is there, which will clean up your switching, right? That filter is related to where the switching frequency is, because the filter it's a low pass filter which will pass 50 hertz and clean up the switching frequency ripple, right? So now if you increase the switching frequency, then that LC filter corner frequency will also increase, and if that increases, it is 1 by root LC, no? So the L and C also will drop, right? So that is the whole idea of making the filter smaller.
Sir, this power grid is in which area, part of Karnataka?
Sir, my geography is very bad.
Because we would like to see that
Yes,
place.
yes. You tell me, I also want to go actually. So we can go together.
Okay.
Well, because I know people who are my colleagues, Sarasij and all, the Gurunath, they are connected. So you tell me, you come, we'll go together.
Okay. Thank you, sir.
Yes, thank you. No, and the thing is that it is one of the largest, I think the largest one in Spain, and this is the second largest in the world. So big deal.
Thank you, sir.
This solar,
Tell me, sir.
this is DC is generator.
You can give him the mic.
Yes.
In solar, DC is generated.
Yes, sir.
How it is? It is converted, inverted to AC.
Correct, sir.
What about the synchronizing parameters?
Synchronizing, no? Right. So, sir,
Is there any provision is there in the inverter?
of course.
synchronize.
Yes.
Up
See,
to 50 hertz.
up to 50 hertz, yes.
Or
So,
beyond that, any deviation or nothing.
sir, 50 hertz, sir, the thing is that the grid frequency will be around 50 hertz, right? It will be between 49.5 to 50 hertz. That's what is in India.
So in that case,
So,
you
there will be a phase lock loop will be there, sir, PLL. A PLL is there which will synchronize. Sir, it is very similar to how you do it in the synchronous generator.
so all the three parameters, frequency, voltage, phase angle, all
All you have, yes,
within the limiter.
yes.
So there is no necessity of PMU in grid system. Phase measurement unit. In Western countries, they are providing phase measurement unit to check the grid voltage, frequency, and all this.
Sir, you
it
can,
will automatically connected to the governor.
right,
So when it is some problem is there, immediately it will like.
right.
Similar arrangement will be there.
You will be there, yes.
In India also we do PMUs.
PMU is already there. PMU is already there. Thank you all for listening, and of course, it has been a great opportunity to listen to you, Kaushik. Actually,
Thank you,
after a long time, we have spent time together, sitting on
Yes.
either side at least. I know you were trying to make it in a language that it is understandable to all of us. So thanks a lot.
Thank you
for
very
making it
much.
so
Thank
simple,
you.
and actually you are actually delivering it to the practicing engineers, which will be beneficial for the whole
Yes,
humanity,
yes,
of course.
yes, yes.
Thank you so much, Kaushik Basu, and we would request Sunil sir to give away the memento, please.
Okay, thank you, sir, for wonderful, because I came in between. Even then, I was, we are asking about the solid state transfer also, because we were hearing it for about last several years. So, whether it is commercialized right now,
But I believe that because of the silicon carbide getting stabilized, 3-4 years we are building 1/2 megawatt 11 kV silicon carbide based over in ISC lab. ISC gives us it is a data ISC collaboration funded by DSC.
okay, thank you.
Thank you. So once the lab is ready, you can come and see.
Hi, viewers.
Open our gratitude. We'll have the next session since we are running short of time. She is arranged outside, so we don't have a. So the another session is carrying on. So thank you.
So the topic technology. They have also arranged a live demonstration of the same along with the that means process bus units and the new digital substation relay which is compatible with 61850 edition 2. So in this session Siemens is supported by Omicron who are handling the testing part of the event. So in this session you can witness the live testing and how a digital substation works and how the testing is done. You can also witness how the merging unit works and how it communicates with the digital relay in the substation. So without wasting further time, we will go to the session and thank you.
നമസ്കാരം എൻ്റെ പേര് സജീഷ് ഞാൻ സീമെൻസ് ബാംഗ്ലൂർ I'm taking care of smart infrastructure product sales southern region mainly especially I'm handling Kerala and Karnataka market. I'm handling medium voltage switchgear, RMU, compact substation, C&R panels, protection relays, RTUs based solutions, distributed automation, EV chargers and cloud applications. First of all, I would like to thank you KSEB for this wonderful opportunity to organizing such an event and providing an opportunity to us to showcase the latest advancement in substation and protection systems. Along with me, our channel partner SK Power, they are in Thrissur. They are taking care of protection and automation products in Kerala market. So Mr. Sunil Paul is here, and our team, technical team is Yoganand, and our he is basically our technical promoter. He is taking care of this presentation, and he will lead the presentation. And our Goa team, Mohammad Jafir and Ali will take you through the detailed demo of the digital substation and cloud application. Now I'll hand over this podium to Yoganand and our demo team, and I'll once again thank you to Mr. Amal sir, and who was coordinated with us and for participating in this event. Thank you so much. And for any queries related to some opportunities or something, then you please reach us, and we will share our number, and for any case you can call us. Thank you so much.
Anything has to be done, connected. From Siemens Limited. And, thank you KSEB for giving an opportunity to present over here our solutions. And as a quickly today, what we are going to see, a quick synopsis of this. First, we will see the before starting this digital substation concepts, functionalities, how it works, and what is the advantages. So we will see what is the latest trends in technologies on protection devices, which will complement and which will carry forward the digital substation applications.
and next you will see the digital twin technology. Currently what we are seeing all are in hardware platforms, so where we are working as a conventional system testing facilities. So the latest technology and trend world going towards is a digital twin. So we are making a digital hardware systems into a digital system, so that it will be easy for those who are into engineering, those who are into testing activities and different users. So that we are going to see. And next is, as you know, now we are in different segments. We are moving towards the cloud-based applications, where those cloud-based applications make our life easier. So instead of our conventional SCADA systems or conventional protection systems, so now we are the technology moving towards the cloud. So everything on handy, everything on mobile applications, everything on web pages. So what is in terms of substation automation or in terms of substation fault management systems, what the Siemens is offering, what is IoT technology, the live demo we can see. And at last we will see about the digital substation testing in collaboration with Mrs. Omicron, who has supported a lot for arranging this testing and facilities. So we will see at the end of this. This is the overall agenda what we are going to see now. So as I told you before, getting into this application of digital substations, we will see what is the advancement in the current protection systems. So we might be seen in many protection devices. I think past 6 to 7 decades we are using the protection relays. We have seen the electromagnetic, then static, then microprocessor. Now we are in numerical era. So the technology or the trend is going beyond the conventional numerical technology. So where our Siemens is offering a such platform of devices we called as Protect 5 devices. So these devices, this is not a one box solution which we have, and this is completely on the modular technology. And modular technology, which I mean here, this can be changed, altered, modified in terms of hardware wise, or in terms of software wise, or in terms of firmware wise. So any stages of the product life cycle, we can add anything, and we can add many more functionalities. You can add the hardware portions. So conventionally, if you see the protection devices, so these are all one box solutions which we had. So once we've installed the system, it has become a single box solution. So wherein we cannot change anything if further, if we found out any operational issues or any maintenance issue, or to enhance the systems. So that is become the difficult in few years, in last few years. Now, so to overcome this modular technology is implemented now. So these are the protection devices which we have, and this is the modular devices which I have explained to you, and this is our base module. So base module consists of power supply and basic LEDs and functionalities and keys, and these are all the add-on modules where you can add based on the application what we have. So this is a completely tailor-made product, or a tailor-made system, I would say, in different applications from the substation automation systems or in the distribution segments. So this can be completely customized. So these are the add-on modules you can completely adding on based on the application. Like we have many applications. We had in a substation, if you see, the transformer protection applications, line protection applications, and the busbar protection applications, wherein So their requirement is evolving nowadays. Sometimes due to operational or maintenance issue, we may have to enable such things after a few years of commissioning activities. So when we use the conventional system with the single box solution, so the adding up the functionalities inside the devices is difficult. So what the Siemens is offering, the modular devices, we can add any functionalities. Suppose if we are using some, say for example as a basic overcurrent application. So we are using some functions now, and later we need to, due to the system enhancement or the requirements, so later if we need to add anything, so either we need to go for a separate devices or we may have to change the scheme based on the requirement. So that was the earlier days conditions. So presently what is happening, based on the modular technology, you can add the number of analog inputs and the number of digital inputs, digital outputs and communication modules, and you can enable the functions in software without the involvement of the OEMs, that is the manufacturers. So those are all the advanced technologies which is coming up, and Siemens is supporting that. And as in the conventional system, the DC system, the DC power is heart of the substation. So currently what we are using, we are providing the DC switching changeover schemes, where if by chance if one sources of power fails, externally we will achieve through a different source of power supply. So there will be some transition times. So what the Siemens is offering, we have a redundant power supply in our device itself. Both are hot and standby power supply modes. So we can give the both power supply unit into the systems. By chance if one fails without microseconds, millisecond transition time delay, so the relay will operate from the other sources. And there is a conformal coating. The recently in our most of our industries, people are talking about the conformal coating and harsh environment protections. So this is like what is conformal coating means. This is like our lamination what we are doing for our ID cards and things, and some important things. Similar to that, the protection devices or IEDs, whatever you can see, either it can be a meters or it can be a protection relays or it can be any other automation equipments. So inside the PCBs are laminated, which means that that's conformally coated. So those conformal coating which will increase the lifetime of the product, and if we use this product in the dusty environments, in most utilities the substations are placed in different areas. So due to the various environmental conditions like salty environments, dusty environments, near to the shores and near to the oil and gas refineries and inside the refinery. So this conformal coating will apply to all the IEDs, and which will increase the lifetime of the system to protect against such the external disturbances or external problem factors. So that also we had Siemens devices, by make it default, this conformal coating is available in all our devices. And the next thing is that we use the inputs, digital inputs and outputs in the different application in the protection devices, where so earlier we are claiming the operating time of 20 to 30 milliseconds of the protection relay operating time itself. So now we have introduced the high-speed binary outputs, which is less than 10 milliseconds of operation, where for the critical applications in the industries and in utilities, where this high-speed output contact is used. So if there is any heavy arc fault, or if there is any evolving fault which will lead to disasters or the worst arc flashing systems, so this high-speed tripping device, tripping outputs are used to disconnect the system when there is a fault immediately. Maybe we are claiming the operating time of less than 10 milliseconds. So if you take the breaker operating time another 30 to 40 milliseconds, on the whole by total 40 to 50 milliseconds we will isolate the system. So when there is a heavy arc in the switchgears, or when we are using any changeover schemes, or when we are using any load shedding schemes in the critical industries, So all our these technologies are coming up currently, and these are, we as a Siemens we incorporated all this by as a default. So this is the overall structure what we are seeing here. And the next thing is the cyber security. So now, as you are aware, in every substation automation systems, so all most of the utilities in the HV and EHV substations, the substation SCADA is implemented, which means that all the critical IEDs are connected in the network, and so that the network is formed and it is given to a one SCADA systems on the substation level. From there, the information will be sending to the transmission control centers. So currently, the evolving of cyber security threats and technologies. So we need to ensure that all the IEDs which is used in the substations are cyber security compliance. So this, as we are doing, it is not like as Siemens is doing, but there is a committee in the IEC where they are continuously checking all the standards in terms of substation automation cyber security systems, and there are different standards. Even KSEB also, they are very much active high in the cyber security terminologies and cyber security studies, which KSEB is interestingly doing many areas nowadays. And as a Siemens, we comply all the standards of latest cyber security, and this can be either we can segregate the hardware wise, the port hardening, system hardening, to disable the unused ports, physical breaches in the substations. In terms of software, there is as I explained to you, we have a lot of IEC standards. So if someone want to penetrate something, how we can avoid. So everything is complied in a protection devices, and we comply with the standards of IECs. So next I'll just play quick some videos. I think sound is there. Huh?
Safety and security inside. Multi-layered protection mechanisms give you maximum safety and availability. The safety concept begins with the SeaProtect 5 device itself. The rugged hardware and an ingenious layout of the entire electronics ensure highest stability with regards to voltage, EMC, climate and mechanical load. Sophisticated self-monitoring routines reliably localize device faults and indicate these promptly, for example, to Dixie 5. Encryption along the entire communication line between Dixie 5 and the SeaProtect 5 device provides the required data security. But the encryption is only one part of a multi-level safety chain. A connection password, according to NERC-CIP and BDEW white paper, protects the remote access to the SeaProtect 5 device. The device itself records each access attempt in a non-volatile safety log, and safety-critical operations at the device device and the system require the input of confirmation codes. Safety and security inside. With SeaProtect 5, that means through the multi-layered protection mechanisms, your plants and systems are equipped with maximum security and reliability. With SeaProtect 5, you absolutely fulfill the newest requirements of international standards and technologies.
So as we have seen, there are multi-layers of protections in terms of cybersecurity before sending any data to the our substation automation. In line with that, so we have some of the standards, like we have the access control, and the access control is like the role-based access. So in a substation there are number of operators, the person who operate the devices, the person who maintain the devices, and the person who is accessing the devices. So everyone has the different access in the system. So there are 5 to 7 layers of password protections, which depends on the user. What is the role of the particular user we can assign. And there are security logging and monitoring information if someone is accessing the devices. Suppose if you are going in a substation, changing something in the settings and viewing what is inside the settings, so all will be updated as a security logs. So that will be updated to the the transmission control center, so that the people in control center, they will aware that someone is accessing it, or someone is in front of the devices and touching the devices. And we have the system hardening, where the ports, the physical ports are equipped with only one-time connection. So if we can unplug and do some other connections, the system will not allow you to access this. And there are malware protections, data integrity, and we have the signed firmware, because someone can create the firmware similar to the protection devices, and they can upload to the devices. So the devices will not accept it, since the firmwares are signed by the concerned authorities. So as I told you, that we have a digital signed firmware, and there are standards which is related to the cyber security, as I explained to you. This 62351, 62443, these are all the IEC standards which they define how the IED should be. So we have to do the periodical testing with the CPRI to ensure that we followed the cyber security. As a Siemens, we did everything with CPRI, and we had most of all the standards which every utility is asking. The certification is with us. And as I explained to you, this role-based access, this is based on the users we can give. And there are some certificate management, because these IDs or these devices are giving the informations to some of the third parties, means some SCADA systems or some other third party software. So we have to ensure that there is a agreement in the what is this transmitted from our side to the system, and what they are supposed to receive. So all these are all the software terms which is we complied as a CCAM grid pass certification. So which is the a software firewall kind of system we had. And as a part of this advanced protection relays, in earlier days we had one devices for one protections. So now we have a system called a universal protection devices. So those universal protection devices, one device, we can configure the multiple application. So the same device, it can be used for the motor protection, distance protection, and for the transformer protection application, and feeders, and the transmission line differential. So there is a flexible functionality in the devices. So where we can configure based on the protection application. So these devices can be used for the different segments in the transmission or the distribution criteria. So where we, in these universal devices, where we have the flexible functionalities. So anytime you can disable something, you can enable something, and if later if you find that you need to disable few more parameters, so anything can be possible based on what we select the applications. So now we'll come to this digital substation concept. So this is called a digital substation, or somewhere it is called a process based application. So what it is basically? What is a digital substation? So conventionally, our conventional substations, either it can be or AIS substations or the GIS substations. So the primary equipments like circuit breakers, isolators, and measuring transformers like CTs, VTs. So all the inputs from the primary equipments and transformers, we are connecting through a copper wire to the protection devices or the metering devices. So that was the conventional system which we are using for many decades. So what the digital substation says. So if you have the lot of copper wires in the systems and a lot of copper cables or the unsustainable equipments, where it leads to a higher in maintenance activities, and during a troubleshooting we are finding very difficult to locate the faults, and maintenance, it's hard process. Years together you have to change the cable, you have to maintain the records of the cables, and you need a lot of spaces in the substation. Somewhere if you want to do any bay extension, there is a constraint due to the space. So to come out with all this, so there is a concept called a digital substation. So these are all advantages. We'll standardize the substation, the digitalization on the station level, and there is a cyber security. Everything is complied with cyber security, whatever I have explained to you on the high level. And where we can manage the asset management. In earlier days, it was quite complicated, and we do the AMCs every year, and we do the periodic maintenance and corrective maintenance and all things. And as a part of digital substation, the asset management processes makes simplified, and the grid operation for the EHV transmission system is very critical nowadays, and those processes make it simplified in the digital substation concepts. And the engineering is easy, and the troubleshooting is easy. As a whole, we are all going towards the sustainable environment, and we are going towards the copper-free environment. Most of the substations, and KSEB also they have installed one of the substations in Kollam. There is a 110 kV substation where it is digitalized. So I would say first is digital substation installed in KSEB only in southern part of the country. So in Power Grid they are installing many substations they are coming up with many projects in 400 kV and 760 kV levels, the digital substation concepts. And what is it? How the structure of the digital substation looks like? So if you see here, one second. So conventionally, this is a substation, high level of a substation, and the connection between the field equipments, like as I told you, the measuring transformers or the primary equipments called circuit breakers and isolators, earth switches. So all are copper wired and connected to the protection devices. So in the digital substation, what we are doing, we are installing a device called a merging units, where we have placed the centralized device. That is called a merging units. So these merging units will receive the inputs from the primary equipment, measuring transformers, or for the transformer application we receive a lot of tap changes information, RTCC information. So everything it will receive. and it will collect the information from the substation level and it will pass the information to the protection relays in digitally, which means that we will run only the fiber optic cables from the switchyard equipments to the control room, or if it is a GIS substation, from the LCC cubicle to the control room we will only run the fiber optic cable. So those fiber optic cable will take the information from the merging units and provide the required information to the protection relays. So conventionally the analog inputs are connected directly. So now these merging units, it will receive the analog inputs and digital inputs and convert it into SMVs, we called as a sample measured values. So convert those current values and voltage values into analog into digital values, and it will pass it to the protection devices. So the protection devices, how it works conventionally, the similar way now also, it will receive the digital form of CTs, current inputs and VT inputs and digital inputs. It will start working in the principle of protection relays based on the application, whatever we had in the substation. So this is the high level concept of process bus or digital substation. So what we are defining here, this is the process level. So on the process level, every bay information is connected with the merging units. So the central unit which we are seeing is the merging unit. Okay, so it will pass the information from the process level to the field level to the protection devices. So these protection devices are connected in turn connected to the SCADA system on the station level. So this level there is no changes. Conventionally what the SCADA is followed as per the IEEE standard of 61850. So the same will be followed here, but only thing we have introduced the extra level called the process level to eliminate all these copper wires. So this is the high level of the digital substation or process bus substation concepts. What are the benefits? As I explained to you, we have use of less copper cables and quicker in commissioning activities, troubleshootings, engineering simple, and the person safety is, because if you have a longer cable gallery, to maintain the cable gallery is quite difficult processes. So to eliminate all this, the digital substation concepts are introduced. So this is on the higher level, the merging units which will collect the information passing to the control room. So instead of copper cables now, in the conventional substation, we are running only the fiber optic cables. So on the whole process, if you see, there are two equipments is involved mainly. One is the merging unit we called as MUs, and another one is the protection devices. So these two devices should be, they should be synchronized first. So what way it is synchronized? The time should be synchronized, because from merging unit we are converting into analog values into digital signals, that is we called as SMVs, and transfer to the protection relays. So both should be, to receive the inputs effectively and accurately, it should be a time synchronized, both should be time synchronized devices. So that is why we had a protocol called IEEE 1588, which they have complied all the time synchronizing processes. Now, as I told you, this merging units will receive all the inputs. So what are all the capabilities of this merging unit? So these are all the capabilities of the merging unit. So it will receive all the inputs from your current transformers, voltage transformers, and it will receive the circuit breakers, disconnector, which I mean here isolator inputs. And for the, as I explained to you, for the transformer application, we have the mechanical troubles like buckles, pressure relief valves, winding temperatures, oil temperatures, and that there is a tap changer control. We have, as you know, in the RTCC panels we have a tap changer control. So those tap changer control also can be integrated here, and we can make all the interlocks, logics, whatever the conventional BCU can able to do. So all this can be incorporated in the merging unit itself. And currently what we are doing it, we are connecting the conventional current transformers, which is a copper based and there are winding based. Currently we have a low power instrument transformer which we called as a LPIT. So LPITs are instead of the physical transformers, they are the completely digital transformers where they use the fiber optic technology to convert the higher current into lower current and giving to the protection device. This is the next level of technology advancement. So those LPITs, low power instrument transformer input, also can be provided here. So what it complies? It complies the different standards, because as you know, this merging unit, it has become a very important equipment wherein it will receive all the analog input, digital input and passing to this device. So we need to have a very stringent standards and stringent technology to be accommodated here. And the first standard is 61850-9-2. So this is the standards for the process bus or digital substation application, where your 61850 defines these are the signals, these are the signal forms. They have a set of rules, process and procedures. So every OEM, including globally, so they have to follow the standards. The first and foremost requirement is these devices are 61850-9-2 compliant devices. And there are others we can have, because if these devices are capable of receiving this analog information, and it is forming a stream, so we call it as a SV, stream values. So those analog, it will be converted into a stream or the digital streams, and it will pass it to the protection devices. So likewise, these merging units are flexible enough to handle a different CTs and VTs equipments. So we can optimize and we can do the engineering to comply with 2-3 bays in one merging units, and we can form different networks by using merging units. And this is the high level configuration. We have different modules, but during testing we'll show to you what is inputs and how it is connected on the back side of the devices. As from the initial I have told you, these are modular based devices. So we have a different combination of inputs, outputs. So see, at Siemens merging units, we have the option to choose the analog inputs, which is around 60 numbers. So 60 numbers is the maximum capacity we had. So based on the engineering and based on the requirement, we can club it to different protections in one merging unit, because the inputs in merging unit receives and it will be put into the stream on the network. So on the network, the inputs are available as a digitally. Now in protection relays, whatever the inputs we need, we will collect it. So by doing all these processes, conventionally we are having a CT core, we have metering cores, we have the busbar differential cores, we have the main one for the main protection cores. By making this digital substation concept, since we have collected the information and converting into digital signals, there is a possibility and we can reduce the number of cores in the CTs. So we can achieve with the minimum CT cores with the maximum effect, and that is one of the advantages. And there are ports in the devices on the merging units. That port we called as a 9-2 port. So that is only will send the information to the protection devices. So conventionally in the normal protection relays, we have only one port or 2 port maximum to connect with the local SCADA in the substation level. So when it comes to a 9-2 compliance merging units or protection relays, we need to have the special ports, which is exclusively used for the substation process bus level configurations, and that port will collect the information and send the information to the protection devices. So likewise, we can make up to the 4 different streams, which means that I can take the inputs and I can give it to the 4 different clients or 4 different users. So that can be programmable, customizable, and we can form like this. There are different, so one merging unit is capable of receiving 4, sending the 4 information with hardware support. So wherein we can configure 1 or 2 protection devices combining with 2-3 base. So similarly, we can do a lot of flexible engineering on this process-based concepts. So maybe while testing, we will show to you how it works. And the next main important things, as we are in the digital substation concept, you may ask the question, if by chance, if what happen if the communication is interrupted. If the communication between the merging units and the protection relay is interrupted, then my protection is lost. So that is why, as a Siemens, we had for protection functions included in the merging units. So due to any unforeseen situations or any natural disasters, if by chance if the communication is failed, because we are using a different redundancy level in the communication, definitely it will not fail by 99%. There are, as a disaster management, some 1 or 2% chances by chance if communication is failed, we will have a backup protection which is inbuilt in the merging units. At the last resort, if something has happened on the communication, unfortunately during that time if there is any fault in the system, so merging units are capable enough to identify the faults and issue a tripping command to the circuit breakers. So at any given circumstances or any worst situations and disaster scenarios, our systems are got protected. So how we can, what is the protection functions are available, that we can, those functions are customizable. So what we want. So as I explained to you, by chance today we are having only 2 protection functions in the merging unit. So we once during we commissioned and later during operational we found out something can be added, something can be introduced newly. So that also can be done through our flexible protection function points. So all the backup protections to the main equipments can be incorporated in the merging units. And as I explained to you, we have 2 power supplies. So power supply also critical. By chance if merging unit power supply fails, my whole protection is compromised. So we had a 2 redundant power supply which will acting as a hot and standby. So if by chance if one is failed, so it will act immediately with the source 2 and it will power on. So the details will stream continuously. And these are the typical structure, and this is an example, and during a case by case we can do the engineering how we want. So this is a typical bay we have a 4 CT cores. So this is core 1, core 2 is for the main protection, main 1 and main 2, and we have a bus bar protection, and there is a metering core. So we can give the individual merging units for the different cores, or we can give one set all the inputs to merging units. So if in this scenario by chance if merging unit 1 fails due to various reasons, so my protection systems will not interrupt because it is getting information through merging unit 2. So similar to this, we can have a complete engineering, and either how we want, how we can customize our systems. So if you see in this case, our complete redundancy is provided, which means that if any such conditions, by chance if the CT secondaries get faulty, or if one power supply fails, or unfortunately by chance if one merging unit got failed, but your protections will not be compromised. So as I before explained to you, we have flexible functions to choose the digital inputs and digital outputs, and the analog value CTs and VTs. So based on our application, we can now customize how we want. So either it can be we provide it this way to have the one-to-one redundancy, or this way. The third is when we use the low power transformer, which I told you, there are optical CTs and VTs in the GIS substations. So that those optical CTs and VTs, it doesn't need any copper wires, simply will connect with the FO cables. So they will talk with SMV values and they will collect the information. So this merging unit placement and doing the engineering, it's completely on the flexible. So this is the typical substation architecture, where this is the merging units, and there are main 1, main 2 redundancy, 2 merging units I have considered. So one bay which will collect information and it will pass into the process bus. And pass it to the process bus, and from the process bus system the individual IED takes the inputs. So from here this is the station bus. So these IEDs are connected to the SCADA, which is for the monitoring and controlling purpose. The SCADA in turn connected to your control centers, transmission control centers. So if you see in the transformer application, HV we have 2 merging units, and LV we have 1 merging unit. So both will be connected to the transformer protection devices. So here if you see, there is one more equipment, main 1, this is a main 1 device and main 2 device. This one more equipment are the BCUs. Those BCUs are used as a bay control units. So those base control unit is generally they will have the interlocking purposes, and it will be connected to the SCADA, which is a separate equipment in conventional SCADA systems. And by introducing our process bus application, this unit can be replaced, since these merging units are already interacting with the primary equipments. So BCU functionalities can be introduced in the merging units. So that also can be possible. So we can reduce one number of devices there, and those functionalities can be introduced. So merging units are capable enough to have critical interlock logics. We can build multiple various interlock logics in different equipments. So it is capable to receive many inputs, and it has the high speed outputs which will be acting fast. So this is a typical connection with the universal protection devices, how it looks. It receives the information and it will pass it to the merging units, and we have the time synchronization. So you may ask question, by chance if my time synchronization is got failed somehow, then how the protection is achieved. So in Siemens, what we have in our system, if already time synchronization will be 2 time synchronization will be provided in every substation. By any chance if this is got failed, and we have an option inside the devices, we can assign per loop 1 device, it can be acting as a time synchronization. So that we called as a grandmaster clock enable. So if we enable that feature in any one of the devices, so other devices, that one devices can be acting as a master, and rest all the devices can be acting as a slave. So that also you can define how is the system you want, how many master clock you want, and based on the number of IEDs, how many slave has to follow in the masters. So we are trying to ensure at any given worst situations in this process bus systems, our protection system and monitoring and control system cannot be compromised. So on the different level of communication and different level of synchronization and different level of hardware and software portions, we cover everywhere there is a redundancy is applicable. And this is a system which I have explained. By chance if main protection is got failed, and we have backup protection in the MU. So during, if main protection fails, if fault has happened, our MU can sense the system, sense the fault, and it will trip the breaker based on the fault conditions. So this is a typical for the transformer application. We can use either 2 MVUs, 3 MVUs based on the application, or we can use the 1 MUs, which will comprise everything, and with one merging unit will achieve both HV and LV protection functions. So all that can be covered. So now in the substation there is a bus bar protection. If you see in EHV substation there are 20 bays, 25 bays. So wherein currently we'll go for a distributed bus bar schemes. Distributed bus bar scheme in the sense every bay it will have one bay units. So those bay units will receive the inputs, respective bays, CT inputs, VT inputs, circuit breaker inputs, isolator inputs. So that will pass it to the centralized units. So that is a conventional distributed bus bar schemes. So in the process bus, so in Siemens, our merging units can also be acting as a bay units. So in this way, we are avoiding one more devices as a bay units for the distribution bus bar application. So this can be acting as a merging unit first and foremost. Second thing, it will be acting as a backup protections, and third, it will be acting as a bay units for the bus bar protection. So as I explained to you earlier, so we had a multiple CT and VTs can be integrated in one devices, so that we can do the flexible engineering to have or to place the merging units in different bays. And this is the typical architecture, how we can ensure the communication between the process or the merging units to the protection device can be formed, how we can avoid such failures. So we have already the proven technology which is in the station bus configuration, that is HSR, so high availability seamless redundancy type of communication, and there is a PRP, parallel redundancy protocol. So these two technologies are already there in the station level communication. Similarly, we can build the same technology on the process level. So here these devices all are all connected in the ring manner. If by chance if one is disconnected, the ring is closing on the other way. So at any cost the communication is not interrupted. This is a HSR method, and another is a PRP where there is a two parallel LAN is formed. So that's why it's a parallel redundancy protocol. If by chance if LAN A is failed or any communication disturbance due to various external factors, so if LAN A is failed, the devices are communicated to LAN B and passing the streams to the protection devices. And as I explained to you, since now we everything make it digitalized, same the cyber security fundamental also applicable here. There are mainly 2-3 standards, the 62443 and the 6235, and you can also Google it and see what it is. So these are the basic 2 standards every IED should comply, and there are some levels of certifications, level 1, level 2. So the higher the levels of certification, the higher the securities as defined by the IECs. So the Siemens devices are all certified with the required levels as per the power grid or as per the KSEB specifications. So I will just quickly go through one of the videos.
This is Tom and his twin brother Mike. Just like all human twins, they seem to be identical to us. In fact, however, human twins are never 100% identical. And how is it with digital twins? With SeaProtect 5, a digital twin is a digital one-to-one image of a real device with exactly equal functions and exactly equal behavior as the original SeaProtect 5 device. For that reason, you can now test the functions and behavior of a SeaProtect 5 device even when you have no access to this device. For example, during engineering or during disturbance analysis. Instead, you use the SeaProtect Digital Twin, and that at any time and from anywhere, because the SeaProtect Digital Twin is located in the cloud. This creates new opportunities, reduces costs, and basically works quite simply. You export the device data from Dixie 5. You establish a connection to the cloud. You upload the device data into the cloud. You are working with the SeaProtect Digital Twin as if it were a real device. And that with your system data, with your test scenarios, with your parameter settings, and all, of course, according to the highest cybersecurity standards. Specific examples. Validate the protection and automation functions of the SeaProtect 5 device. Test the boost communication between two devices. Or check the communication interface to the station automation. For all that, you merely require a PC or notebook with any browser you like. And then, connect. Log on. Get started. This is easier than a test setup. Faster than driving to deployment. Less expensive than the investment in test devices.
Okay. So what I'm trying to say here. So initially I've explained some of the concept called digital twin, where so I'll highly, due to the time constraint, I'll highly explain in a detailed way, in a high level way. So whatever you're seeing here, this is the physical devices. So these physical devices are placed in the substation. So if you want to do anything, if the bay is in service, you cannot access the devices. And you want to do any testing on the devices, you want to know how the device operates in different system conditions, or you want to train your people. How do I train the people? Because when the device is in service, you cannot access the device for the training purposes. Or you want to see how the device is performing. So for all these you need to have the hardware devices. So what the digital twin technology, nowadays it's digital twin become a common word which is applying to different industries, different segments. In our substation automation field, we are making digital twin of the hardwares, that is a protection device. So we will have a web-based application. So whatever the physical device you are going to work with, so the same replica we are creating in a soft, in the web-based application. So where you can interact with the devices, how you are accessing with the devices physically, and you can see the performance of the devices. You can test the devices. So if it is the station is charged, the devices you cannot do any testing. You want to see some of the functions operation. By using this tool, you can simply access the devices and see how it works. And by chance, if somewhere else in northern part of Kerala, if any bay is got faulty and any bay tripped due to some functions, you want to analyze by sitting in Thiruvananthapuram or in Kochi. So how do we do that? We can take the files from the devices. We can create a similar files in the soft setup. We can run the files, especially we called as a ComTrade file, which we collected from the site or the substation. We will play here and see how the relay responds. And in one step ahead, so like what we are calling as a digital twin, the test kit peoples like Omicron, so they also have the digital twin concepts. So we are collaborated between us and we can test the devices virtually. So without having the physical device. Obviously on the substation you have to do the basic testing, basic hardware testing, inputs and output taking, so we cannot compromise on that. but the processes, this digital twin helps to reduce our timelines. So conventionally, if you do test setup, FAT, travel and testing, so with digital twin, you can reduce significant 30 to 40% of your time. On these devices are 24/7, it is available with you. If you want to train your operators, if there is any fault happens, if they cannot access the devices physically, since the system is new, so you can take a class in this digital twin application where you can show how we can access, and you can create a virtual network by using the concerned VPN. So you can have 3-4 devices together in one platform, and you can test the Goose application. You can test the SCADA 6950 signal application. So it is nothing but simply as the physical devices. So if you see the new project commissioning, so the classic process, if you see, you have to do engineering, testing, mounting, installation, commissioning, everything. So with the digital twin, what we do, engineering, testing can be a one process, and mounting, installation, commissioning. So before entering into the commissioning, we are ready with our files, we are ready with our data, we are ready with our test results. So once the commissioning takes place, we will simply go and install the devices and do the basic hardware testing, and this is ready for the commissioning activities. So as a utility, how it helps? As I explained to you, for the fault analysis. So you want to, suppose one other OEM device is got tripped. So without device, you want to see Siemens device, how it is reacted to the fault, which is sensed by GE device or Hitachi device. So you can take the files and play here and see how it works. You can do the analysis whether both the devices are operating correctly. Is there anything we have to do in our system, or any fine tune is required or not. So all this can be done by using the digital twin. And so if you see, this is our conventional step. You have to test with the kits. Of course, the testing is required on the hardware portion. There is no compromise on that. But before testing, if we can do the logics finalization, setting finalization, everything in digital twin. So when it comes to the testing, so our troubleshooting time will be less. So when it comes to the testing, we will be prepared around 60 to 70% will be prepared, and rest is only 30 to 40% of the testing will do, and will save the time. So this is all the latest developments happening in substation automation system, and my colleague will take you through this cloud-based application, and how is nowadays. Jafir, you can go do the setup. By the time I'll explain high level. Nowadays, what we are doing a substation automation system. All the substation IEDs are connected with the SCADA. So you are monitoring in the SCADA, and you are monitoring the current voltages parameter, and you are controlling also from the SCADA. So currently what is happening, due to the sizes increases, the substation size increases, the number of base sizes increases. So the IoT is providing an opportunity to connect all these IEDs into a cloud. So we can make a virtual SCADA on the cloud application. So all the IEDs is connected to the SCADA, which will display in the cloud application. By sitting in your home, you can see on the substation what is happening. What is voltage trends and what is the current trends, what is the events, if some slow evolving fault is happened, what is my event, and if someone is accessing the relay, you will come to know from the home by accessing the mobile application or the web application. So if you are having the 2-3 substation on the location wise, so every location has say 15 to 20 IEDs approximately, as an example. So if you click the location, all the IEDs will display, and by sitting in the home, you can see, you cannot control anything, but you can monitor like what we are doing in the SCADA. You can monitor the voltages, currents, you can monitor the events, you can monitor the who's accessing, if someone is changing the settings, immediately you will get a notification if someone has accessed the devices. So Jafir, can you just go through this? And this is the cloud-based application where the information is not going to anywhere in India. Sorry, no, not anywhere outside the India. So we have our own servers in India, AWS Mumbai. So this information are 2-3 levels. Firewall system is there. So once we collect the information from IED, there are 3-4 firewalls and 3-4 certification. After that, it will be stored in the cloud servers. So you have given the access. So based on the roles you are placed in the utility. So once you access the system, then you can able to see the complete IED details and things like that.
Hi, good morning all. I'm Jufan Office. I'm basically from Kerala only. I'm working in Goa factory, like customer support. So I'm very proud to be here. I'm facing to very senior people, very experienced people here. So I'm happy that KSEB also there with our new features, and they are going to be with the new trend. Okay, so basically I'm going to show you the electrification X. So this is a cloud system actually. As Yoganand said, we can get all the details in cloud. Either if you are in home or if you are sitting in anywhere, any of the corner of the world, you will get the data. So basically, this is the cloud system we are having. So this you can log in from either your laptop, either your phone, a tab, anywhere you can open this web page. And this data is only in India only. It will not go to out of our country. So basically, you can see the overview. This is the overview. Wherever the substations you have placed, that you can locate according to the, if suppose this is the one station we have placed for demo purpose.
So geographically you can, suppose in Kerala itself there are 3-4 substations. We can make a configuration, geographically it will display on the locations.
Yeah. So if we go to the substation, the right side of the corner you can see all the fault, like whatever the events came, all details you can see. So if you wanted to go through the if suppose you take this district only, means this is Kollam, right? Kollam, if you take, there will be substation 1 or 2, 3 substations. Each substation will have different feeders, and each feeder will have IEDs, meters, all things. So we wanted to get to know all the separate device details. That is also possible here. So for that, I will give you a brief review of the electrification X. So overview, this is the overview page, and here you can locate the substations. Then for events, there is another option called events. If you come here, you can see the events. It is the substation, as I told. Here, what is the current status it is came, it will be visible here. And if you go to the assets, here in assets we can manage, like if it is in a substation, the feeder wise we can manage here. And in each feeder, how many devices are there, that is also we can classify here. And incomer ways, incomer details and outgoing details, all this we can check here. And accordingly, here we have dates also, which date, from where to where, that also we can filter and we can take the data. And as Yoganand said, there you will get the device data. If you see here, you can see IED. It's a Siemens relay, and you can see the make and what is the firmware, currently running firmware. All the details you will get from here. If someone is updating the firmware there from the station, that is also will be updated here. And one more thing is protection settings. That you can see here in the protection settings. What are the protection settings have available here? That also it will be visible here.
So this is not only a Siemens devices where you can see the list of devices. So whatever may be the different OEM devices, whoever supports the 6.50 communication protocol. So this device, this tool can be integrated with the devices. So if you see the 442, these are all GE devices wherein we can integrate it in this tool. Go ahead.
Then we will get the fault reports. If you come to here we have even PQ meters also. In PQ meters there will be a trend report, those details also which will be available here. You can even filter out which date you wanted, and here if you come, there is an option to download the events also. If you select any event, you can download, and there is a separate software is required, means a separate tool is available with the software, that if you have that you can load and you can check the variations, everything you can visible here. Then next we have one more interface here called overhead line faults. So if you come to the overhead line fault, I will just open that. Basically, we know these days there's power outages, like we have to, all the states are trying to be reduce their power outage. So for that we are implemented FSI FCG, fault sensor indicator and fault collector gateways. So basically what it will do, it will reduce your patrolling time and the power outage time. Directly you will get a message or a mail to your phone, then you can understand where the exact location of the fault. Because in higher like 33, if you go above 33 kV, there will be distance relays kind of. So here that same work it will happen with the FSI also. So FSI, if you are implementing in a line, in a 10 kilometer line, if you are implementing, it will be like a mounting device. You can mount over your headline. So if you are mounting that, you will get if any fault like phase fault or a DI by DT fault, you will get a message into your phone. So your patrolling team, you can get them directly. You can go there and you can fix that any breakage or something like that. So in that is also linked with our electrification X. Here also you will get to know which location it is, and you can directly go to there and you can clear the fault. And here also we have options like just 1 second. We have set up like permanent fault and temporary fault. Actually there is a PFVT time, so it will consider like the verification time will be there. The FSI will be delayed for that much time, and it will understand, okay, this is a permanent fault or it is a temporary fault. Kind of information also and kind of messages also you will get here. You can see that some of them are permanent fault and some are the temporary fault. It came in different dates. That dates also you can filter and check. And there will be another option like as I told, phone call. You will get a phone call directly to your phone. Like you can assign the phone number of your substation in charge or the patrolling team. You can assign that. They will get direct call from the device. I will show the settings of that also. Here you can assign. There is an option called email configuration option also is available, and phone number also is available. So basically you can get, if you are assigning a mobile number, directly you will get a call plus a message you will get. If you are ignoring the message, if you are not seeing that, repeatedly after 5 minutes, 10 minutes you will get another call to ensure that. And there is a fault analysis also. I will just show you the fault analysis record, how it is working. In this graph will explain you in a month or in a year how much of permanent fault came and various locations. Sorry. So you can see the summary of the the device will give a summary, like in this month you got this many fault, that is permanent fault, how much permanent fault, how much temporary fault, all kind of things. It will by default the app only will calculate and you will get a graph like this. So these are the main advantages of the Electrification X. It will reduce your time and you can access from anywhere. And the patrolling team, their timing also you can reduce. And even the cost of even if you are going for a patrolling, you have to, if it's 10 kilometers, you have to travel all around the 10 kilometers. That is also you can avoid. And even power outage also you can reduce. So these all are the main thing about the Electrification X. Okay, thank you.
Thank you very much. If there is any doubts, it's...
Is this what you are talking about?
No.
This is a distribution overhead fault management.
No. Electrification X. Electrification X is the concept of digital.
No. Electrification X is a concept of cloud-based application, IoT applications. So conventionally what we are doing is we are doing an all on-premises solution.
Suppose if I want to access this digital,
Yes.
Is it possible without a license or anybody can?
You have the free access. Every day you will have 15 to 20 minutes free access you will have. So that is a free access, you can use it n number of times. So if you want a permanent access, then you need to have the license.
This one comes with the Dixie 5 or?
No, this is separate. Separate. Yeah. This is a subscription based license. In a yearly you have to renew it's like our Netflix subscription simply.
Okay, then we can do the engineering configuration, everything in the digital twin.
Everything in digital twin. You can export the file from the digital twin.
To the basic unit.
You can export the file, and the same file you can import in the physical device. For the time concern, I cannot show you the live demo, otherwise I would have shown the live demo. And if by chance if this device you want to see in the digital twin, just simply you export the files through Dixie, and those files you can import it here. So once you import it, whatever you have seen in the physical device, same you can see in the hardware also. ComTrade file, suppose you want to play the ComTrade files. So you from the site you will receive the ComTrade file and you can play in the digital twin.
So original device to digital twin and digital twin to original device.
Yes, it's vice versa is possible. You can do the complete configuration in digital twin, and testing also is possible. The basic testing is possible with our digital twin, and if you are the closed loop testing like distance protection testing, and we need to collaborate with the test kit manufacturers. They also have the digital twin. So those digital twin has to be talk each other with the required VPN connectivity and as well as the cyber security features.
So if you want to get the subscription, what is the procedure?
So subscription we can offer you. You want how many for a year or 2 years, 3 years? Start from a year basically, and maximum is 5 years. One time you can get in a subscription.
For 1 year, how much you are charging?
That maybe I'll check up with our team.
I only taking care of that part.
The cost portion he will let you know. You can see per day 15 minutes is free. You type in Google Ciprotec Digital Twin, this one, you can have the look and feel how it looks, but to upload there you need to have the device file. So once that is a one-time process. Once the device file is enrolled, then there is the testing itself. You can do the basic current injection, voltage injection testing, and you can do the COM file analysis like a transplay what Omicron is offering. You can do the in digital twin itself. There is a transplay. You can do the transplay, and binary inputs, binary output configuration complete. You can access even Dixie 5 through the digital twin.
So we can make a CFC logic and everything.
Everything. There will be virtual page will be open for the Dixie 5.
And for this electrification also, say, this is also separate platform. You need any license?
Yeah, this is also subscription based. So this is electrification axis little bit on the substation automation, how we are seeing substation automation. So the same way you can see in the cloud, but it depends on the number of devices, how it is. And
Map our asset in your web.
yes. Only we are not mapping it, only we are collecting the information of your IEDs. That's it. And we collecting the information from your substation and we are making as a dashboard.
So from IED, we have some communication with the net.
No, we don't need any special communication. For the SCADA, you might be having the network. Correct? No? With the same network, with the same switch, I will take one spare output. That's it. I will put one IPC, simple IPC, and that IPC with modem. So that IPC will pull the data and pass it to the cloud through modem. So once only the hardware portion, only this is the requirement.
So once you take from each substation, this location of substation automatically will go
Fetch in, we can fetch into this.
automatically.
No need to, no. So in between we have a 4-5 of firewall systems. I am taking the devices information from the station and will pass through the 4 checkposts, in the simple language I would say, on the firewall system in order to have the clear data and protected data. So, and it will go into the cloud now, Siemens server. So every time when you access, like every time when you access the portal, you will access the cloud information. This is completely like a bank nowadays what we are using internet banking. Similar to that, this information will be on the cloud. If any time you need, you can own access. So only here the main very important thing here, you can download the COM file sitting in your home.
Sir, here we are talking about digital. That is a cloud-based system. Okay, wherein this Protect 5 series having a feature called virtual simulation, wherein you can take out the relay which as a virtual and you can test it and.
So in Dixie's 5 software you are saying, we have a virtual simulation. Basic current and voltage injection facilitation is there. So once you prepare everything, you are preparing some logic, CFC, so you want to test something and you can inject the current and see in Dixie 5 itself. That is a localized on-premises solution.
അത് എന്തിനൊക്കെ യൂസേജ് ആവുക വെച്ചാൽ നമ്മളിപ്പോൾ ഈ റിലേ നമ്മളിപ്പോൾ ലൈവ് കണ്ടീഷനിൽ ഇരിക്കണം. അപ്പം ആ സമയത്ത് നമുക്കിപ്പോൾ എന്തെങ്കിലും ഒരു സെറ്റിങ്സ് ചേഞ്ച് ചെയ്യണം. അതായത് അത് സർവീസിൽ എടുക്കാതെ നമുക്ക് ടെസ്റ്റ് ചെയ്തിട്ട് നമുക്ക് സിമുലേഷൻ ചെയ്ത് ചെയ്യാൻ പറ്റും. അതിനിപ്പോൾ ഈ ഒരു ടെസ്റ്റ് കിറ്റ് പോലും ആവശ്യമില്ല. നമ്മൾ ജസ്റ്റ് റിലേ നമുക്ക് ഒരു വിർച്വലായിട്ട് എടുത്തിട്ട് നമുക്ക് ടെസ്റ്റ് ചെയ്ത് പ്രാക്ടീസ് ചെയ്തതിന് ശേഷം പ്രാക്ടീസ് ചെയ്തത് നമുക്ക് ഓക്കെ
To ensure the logic is correct, your setting is correct.
ലോഡ് ചെയ്യാൻ പറ്റും. അത് ഈവൻ യു ക്യാൻ ടെസ്റ്റ് ദിസ് റിലേ ഫോർ യുവർ നമ്മുടെ എഞ്ചിനീയേഴ്സിന് ടെസ്റ്റ് ചെയ്ത് പഠിക്കാൻ വേണ്ടിയിട്ട് പോലും യൂസ് ചെയ്യാൻ പറ്റും. കാരണം ഇപ്പം ഒരു ഇത്രയും വില കൂടിയ റിലേസ് നിങ്ങളുടെ ഇപ്പോൾ ഒരു ടെസ്റ്റിംഗ് ടീമിന് കൊടുക്കുക, അവർ പഠിക്കുക എന്നൊക്കെ പറഞ്ഞാൽ ബുദ്ധിമുട്ടല്ലേ. അപ്പോൾ പക്ഷേ നിങ്ങൾക്ക് ഇത് വിർച്വലി എടുത്തിട്ട് നിങ്ങൾക്ക് ടെസ്റ്റ് ചെയ്തിട്ട് നിങ്ങൾക്ക് കാര്യങ്ങൾ നോക്കാം. അതിൻ്റെ അങ്ങനത്തെ ഒരു അഡ്വാൻറ്റേജ് ഉണ്ട്.
And these devices are web-based. We have web UI portability also. Every time, no need to go to Dixie 5 softwares.
Right.
Simply, if you can type the IP address in web page, you will open everything.
Through web page, read and write option is there.
Read and write option is there.
ഞങ്ങളിപ്പം KSEB ഇപ്പോൾ CRP SAS കേസിനൊക്കെ പോർട്ട് ചെയ്യുന്ന നമ്മളെല്ലാം പ്രോഡക്റ്റ് 5 ആണ് പ്രപ്പോസ് ചെയ്തത്. വിർച്വൽ സിമുലേഷൻ എന്ന് പറഞ്ഞ ഒരു ഫീച്ചർ ഞങ്ങൾ ബൈ ഡീഫോൾട്ടായിട്ട് KSEB ഞങ്ങൾ കുറേ കേസിൽ നമ്മളിത് പ്രസൻറ്റേഷനും കാര്യങ്ങളൊക്കെ കൊടുത്തപ്പോൾ ദർ ഓൾസോ ഇൻട്രസ്റ്റഡ് ഇൻ ഡൂയിങ് അക്സെപ്റ്റിംഗ് സച്ച് ടെക്നോളജി. അപ്പം നമ്മളത് പ്രപ്പോസ് ചെയ്തു. അതൊരു വൺ ഓഫ് ദ ഗുഡ് ഫീച്ചറാണ്. എന്താ പറയുക, ടെസ്റ്റ് ചെയ്തിട്ട് എന്താ പറയുക സെറ്റിങ്സ് ഒക്കെ ഓക്കെ ആണ് നമുക്ക് ലോഡ് ചെയ്യാന്ന് പറയുന്നത് ഒരു നല്ലൊരു ഓപ്പർച്യൂണിറ്റി.
This electrification will be working in any other make SAS system like G or
Yeah.
We
Other make IEDs.
other make SAS system.
No, we here in Electrification X, we are integrating only on the IED level.
Sir, earlier our reciprocal dashboard.
Yes, yes, yes.
Sir, that we have changed it to electrification. Earlier it was called as S2L, it was reciprocal dashboard. So, IEDs, make IEDs. That can be communicated to the...
So, the IED which supports 6150 will be integrated here. So, no need having the separate hardware. Already your station is networked. The only thing I will take the spare ports and I will connect one IPC and modem. No. You have integrated, na sir.
Okay.
So commonly before into a SAS HMI or through 104 control center HMI, you will have a common network switches. So by anyways, I need to have the networking to be done. You might be having three, four network switches. That is fine for me. Finally, one output I need from your common networking switch.
Criteria IEC 6180
Yes. We have to add IED details. No, it will not automatically fix, sir. You need to do like your database creation in the SAS, one-time activity has to be done. If you have readily ICD...
Because in the presentation you have said that it is already existing. Okay.
No, this is a demo system which you have shown.
It is better how we are adding, how we are...
No, we'll have a separate session on this, sir. If you are interested, we'll come and we'll give you how it works. A separate session we can. It's as simple as similar to the SCADA system only. SCADA system, they do the on-premises solution. Here we are doing in the cloud.
Digitalization, that particular portfolio, you can able to communicate, or you can see everything in a station level, substation level, or in the this RMU connected network, wherein this RMU will be located in various locations. Right? It will be very difficult for you to go and check healthiness or anything. So this can be communicated and it can be monitored and documented system. And also this fault locator, FSI, FCG. അങ്ങനത്തെ ഒരു ഡിവൈസ് ഉണ്ടല്ലോ. ഇപ്പോൾ KSEB തന്നെ ഒരു FSI എന്ന് പറഞ്ഞൊരു സൊല്യൂഷൻ ഉണ്ട്. ഫോൺ പാസേജ് ഇൻഡിക്കേറ്റർ ഓവർഹെഡ് ലൈനിൽ യൂസ് ചെയ്യുന്നത്. ആ സിസ്റ്റത്തിൽ ശരിക്കും അത് ഞങ്ങളുടെ സിസ്റ്റത്തിലെ വർക്കാവുള്ളൂ. പക്ഷേ ഈ ഇലക്ട്രിഫിക്കേഷൻ എക്സ് എന്നുള്ള ഒരു പർട്ടിക്കുലർ ഇതിൽ ഇപ്പം നമ്മുടെ ജാഫർ കാണിച്ച പോലെ ഈ ഡിവൈസിന്റെ ലൊക്കേഷൻ വൈസ് നമുക്ക് എല്ലാം ഫോൾ ലൊക്കേറ്റർ, ഫോൾട്ട്, എന്തൊക്കെ അനാലിസിസ്, അതിന്റെ ഡിസ്റ്റർബൻസ് റെക്കോർഡർ, അങ്ങനത്തെ ഇൻഫർമേഷൻ ഫുള്ളായിട്ട് നമുക്ക് മോണിറ്റർ ചെയ്യാൻ പറ്റും. അതാണ് ഇതിന്റെ അഡ്വാൻറ്റേജ്. അപ്പോൾ നമുക്ക് സബ്സ്റ്റേഷൻ, ഒരു ചെറിയൊരു സബ്സ്റ്റേഷനോ അല്ലെങ്കിൽ ഏറ്റവും മെയിൻ സബ്സ്റ്റേഷൻ KSEBക്ക് അങ്ങനെ വേണമെന്ന് വെച്ചാൽ ഇംപ്ലിമെന്റ് ചെയ്യാം. അല്ലാതെ ഈ RMU ഇപ്പോൾ വലിയൊരു നെറ്റ്വർക്കിന് വേണമെന്ന് വെച്ചാൽ അങ്ങനെ ചെയ്യാം. ഇപ്പം നമ്മുടെ കൊച്ചി, തിരുവനന്തപുരം, കാലിക്കറ്റ് അങ്ങനത്തെ ഏരിയയിലൊക്കെ RMUs ഫുള്ളി നെറ്റ്വർക്ക്ഡാണ്. അപ്പം ആ സ്ഥലത്തൊക്കെ നമുക്ക് ഇതേപോലെ ഡാറ്റ ഫെച്ച് ചെയ്തിട്ട് നമുക്ക് ഇത് ചെയ്യാൻ പറ്റും, ഇങ്ങനത്തെ ഒരു സൊല്യൂഷൻ കൊടുക്കാൻ പറ്റും. അല്ലാതെ പിന്നെ ഈ റിമോട്ട് ഏരിയയിൽ ഭയങ്കരമായിട്ട് underground cable.
We have FPI, sir. That is a different product. That will be placed in the RMU.
Fault passage indicator. അതിൽ ഇപ്പോൾ സാധാരണ ഇപ്പോൾ എല്ലാ നെറ്റ്വർക്കും, അതായത് കൊച്ചി, കാലിക്കറ്റ് ആ ഏരിയയിലൊക്കെ എല്ലായിടത്തും FRT യൂസ് ചെയ്യുന്നുണ്ട്. അപ്പം അതിൽ ഓൾറെഡി ഒരു ഡാറ്റ കളക്ട് ചെയ്തിട്ട് ഇരിക്കുന്നതാണ്. അത് നമുക്ക് ഇതിലേക്ക് കണക്ട് ചെയ്യാൻ പറ്റും. അപ്പം ഒന്നും കൂടി ഈസി ആയിരിക്കും. ഇത് മറ്റെന്താ നെറ്റ്വർക്ക് മറ്റേതായിട്ടുള്ള സ്ഥലത്ത് കൂടുതൽ RMUs ഒക്കെ യൂസ് ചെയ്യുന്ന സ്ഥലത്ത് അങ്ങനത്തെ ഒരു സൊല്യൂഷൻ നിങ്ങൾക്ക് യൂസ്ഫുൾ ആവും KSEBക്ക്. അത് ഞങ്ങളൊരു ഡീറ്റെയിൽഡ് സെഷൻ വേണമെങ്കിൽ
we will have detailed session, sir. We will have this. You might be heard this SOG, self-optimizing grid, on the RMU level. So if your RMU is a smart RMU, which means smart means your RMU is installed with the FRTU, we can form a ring network, and based on the outages, it will give you, it will open the other, it will close the other loop. So we call it as a self-optimizing grid, and we will have maybe a separate session on that. We have introduced in Tata Power Delhi, many places. That we can. We recently got a performance certificate from Power Grid. And
for the digital substation.
For the digital substation.
And we are proposing this similar digital solution in various locations in KSEB. KSEB also asked for the this proposal and all that, which is going on.
Which substation?
See, we have already proposed.
No, with PGCL, which substation?
PGCL, sir, Malarkotla in Punjab, we have installed and we have got a performance certificate for 400 kV. And Power Grid Navsari in Gujarat, 2 weeks back, it has got commissioned. It is the largest digital substation in Asia, which is of 765 kV. No. You mean to say you can replace the physical device into soft? No, that is not possible.
This relay has to be connected to the cloud. Yeah.
On the specific topics, if you have any interest, we have a separate technical session also, because this we can talk in half a day every topic. We have that much information is there.
So can you talk about the time synchronization? Without a GPS clock, can you manage the network?
Yes, that is possible, sir. Without a GPS clock in digital substation, our BU merging units and the protection device has a inbuilt Grand Master Clock, GMC we called. So we can decide, suppose if it is in HSR loop, per loop one device we can decide as a Grand Master Clock. So that Grand Master Clock shall be followed by these merging units.
Any GPS is there?
No, it is not a GPS, sir. It is like on the moment the time is got disconnected, the Grand Master Clock will be enabled. So that time is synchronized with downstream devices. We don't have any GPS arrangement in the device, but based on the timing at the moment of GPS disconnection, the timing is a reference time.
So you told in the network 8 sampled values like that in the network. Maximum 8 SME.
So we can make different SME streams.
SME stream.
Up to 8 SME streams we can send the informations.
That means analog and digital or analog only?
No, both, sir.
So only 8 streams. In each streams, how many digital data you can?
No, that is unlimited. Means we cannot have any control on the device. Whatever the currently what we follow, the required information will pass through this SMEs.
So one SME stream, how much data it can carry?
No, that we are not defining the number of SME values. It depends on the number of the devices which we connected, number of clients, and we don't have any specific on this.
So we are running short of time.
Yeah,
So
please. Thank you.
we'll wind up.
Maybe we will have a separate session on
Yeah,
this.
how can you arrange it like?
We will have
request we will arrange. Yeah, you request to the board.
Yes.
Okay. And for any queries related to any opportunities or something, you can reach us and we will shortly share. Okay. So thank you so much.
Thank you.
Narayana and Papneja from Omicron. So I hope it will be a wonderful session. In the afternoon session, we will go into testing, actual testing.
Yeah, so very good afternoon everyone. So Mr. Papneja was unable to be here, so this is Manish from Omicron. So I used to take care of the part of data substitution testing, so I'll be presenting this most of the thing, and then Narayana will present about the CMC 500 and other things. So already Yognath has given an idea about the digital substation. So if we are having a substation, we also have to do the testing part also, right? So for testing part, Omicron does have a lot of solutions for that. Maybe I'll take you through for whatever the solutions, what Omicron has it and what we are doing it in the digital substation testing related things. Before that, I'll just give you an idea. Omicron is very, even we were associated with this 6150 things at a time where in India no one is talking about this digital things. Right, so in 2021, this is the demo setup which we were having it in Vancouver with testing a digital relay at that time, right? And we are very much, our team is associated with this working group 10, IEC working group 10, which was earlier before the 6150. This is the working group was there, and then this got converted into 6150. Then we, as Omicron, plays a big role in authorizing this authored that 9-2 LE in standard for sample value publishing simply, and this 6150-90-4, this is mainly related to the redundancy protocol in digital substation like SSR, PRP, global synchronization, those things. Omicron plays a big role in authorizing those documents for this standard. And our team is into this UCA international group, testing group, and SIGRE B5 group also. So we are very much well into this definition of 60850. Already Yognath has given an idea about digital substation, but this is a brief introduction of digital substation and comparison between the conventional substation and modern substation and a complete digital substation, right? So conventional substation is nothing digital exactly, so even the CTPT is everything. If I take it like this is the conventional substation where everything is coming hardware connection, right? CTVT inputs are coming to your bay level IDs, bay level IDs are connected with a copper wire connection where current and voltage is coming from that, and then this bay level IDs are connected to your station level things, all are again copper wire connected, and then to your HMI and to your station level. And there is a upgrade, this is a convention, and this is a kind of a hybrid substation. So in hybrid substation, mainly the current and voltage, again the same CTVTs which was used earlier, the same it is used into this hybrid substation also, but in between the bay level and the field level switch gears or CTPTs, there will be a merging unit. I think that is why this merging unit can be used. So merging unit can receive the value in the form of analog values, and then it will convert that into the digital form to give it to the bay level. The main difference between all three of them is that if you talk about complete digital substation, nowadays the CTVTs directly can give the output in the form of digital values. We call it NCITs, non-conventional instrument transformers. So we don't require merging unit in between in that case, and directly from the CTVTs it can give input to your IDs by connecting a fiber optic cable. So that's the main difference. So again, in a substation there are multiple kind of communications happening. So between the different IDs, one kind of communication, between the different levels of your substation, station level, bus level, and process level. Right? So there are different levels in a substation. So between the different levels there is one kind of communications. For example, CTVTs, right? CTVT is communicating between this CTVT to the IDs. So this is one kind of a communication. Then goose communication, between the peer-to-peer communication, we used to call it between ID to ID. Then for if any control, if you wanted to do it from your HMI or to your control center, then this is also one kind of communication. If you wanted to configure something, then again one kind of communication is required. So there are a lot of communications happening. So why am I giving you the information? Because we have to test these communications also, whether it is happening correctly or not. About the background of what we have in Omicron, we have a complete solutions for testing any digital substation. So maybe skip this slide because it would take some more time. Give you an idea about communication, as I said. So one of the communication what happened in a substation is the multicast communication, where the information will be sent by one ID or maybe one tool that will be published to every single ID. So whosoever wanted to subscribe that, or it is defined for that ID that they will subscribe that and they will work on that information, they will subscribe it. So if I place an animation, so this ID 1 published one signal or information to the network, and this flows to every single ID, every single device connected to the network. So this is called multicast communication. Maybe one example I can take, if you are at a railway station, the guy from the who is doing the announcement, right? He is announcing that this train will come to this platform. So if you are going to take the train, you will only go to that platform and take the train. Others will only listen it and leave it. They will not go to that platform. So this is kind of a multicast communication happening in substation. So mainly the multicast communication example which were happening, the signals which are very critical, those are multicast communications. For example, the goose communications or sample value publication. There should not be any delay in between, right? There is a defined time in the standard also, there should be not delay. So that's why those communications are happening through multicast communication. Then there is one more type of communication, client-server communication. It's one-to-one communication. So one party will be the client, one party will be the server. So whenever client wanted to know something, he will ask the server, he will share the information to the client, and they will get to know that yes, both parties got the answers. So if I play the animation now, so maybe this SCADA asked a question to this ID sent the information to this SCADA. So no other ID getting that information, what exactly this SCADA asked to this ID and what information it has shared to this SCADA, because it's one-to-one communication, right? So this is also one type communication. But again, example if I take is the control from your HMI or SCADA. If you are controlling something, it's one-to-one communication happening. Next, sample value, because sample value goes, as I said, it comes under the multicast communication. So sample value, why it is there? Firstly, we are moving from analog to the digital part, right? So we have to convert the values from analog values to the digital form. So sample values is the digital form of the current and voltage. And how it is converted? So one is that you can use the merging unit, like the middle device Siemens has placed. So using the merging unit receives the value from the normal conventional CTV. It is in the form of analog, and it converts it into the digital form. And one of the standard for publishing the sample value is that 9-2, right? 6150 9-2 sample values. There are different frequencies, there are different packet information are there in the standard. Depending on your application, depending on your need, you can select it. So the first two is one for 50 Hz, one for 60 Hz, like 4000 Hz sampling frequency. That is mainly for protection metering used, but when it comes to 12,800 and 15,000 something, that is mainly for power quality measurement. If you want to do that, those kind of sampling rates are required as per 9-2 LE. So there is one more standard for sample value, that is 61869-9. This is mainly the standard of instrument transformer, because as I said, there are nowadays the instrument transformer also a complete digital, means it directly convert the value in the digital form. So this is that is standard 61869-9. Okay, so this is the sample value. Now goose, as I said, goose is also is like a multicast communication, right? So in this case, it is published as a multicast message, and there will be no confirmation. But now there are things in place where you can also get a confirmation for whether the goose message was received, subscribed or not. It is mainly one party will publish it and another party will subscribe it, but publishing will be for everyone. Whoever wanted to subscribe it or define for subscription, they will only subscribe that message. And what is the motive of having the goose is simply replacing the copper wire communication cables connected between the different IDs, like the binary output of one relay is connected to the binary input of one relay for some kind of scheme or logic or some tripping the breaker or something like that. To replace that, this goose thing is in place in the standard. So that is what the main motive, to replace it from the. Okay, so. So mainly the main motive of having to replace the hard wiring connections which is there in the conventional substations. Now, these are the applications. Faster for any interlock scheme, if you want to do that, then again it becomes quite easy, because on one Ethernet cable all the goose information is flowing to your network, and then things are quite easy. Otherwise, in conventional substation, you have to connect every single copper wire to binary output, binary inputs, logics, right? That becomes quite difficult. And now the testing part. So digital substation, already he gave a background, little bit of background I gave you. So now how to do the testing at digital substation. If I take only the example of a relay, like testing one relay, nowadays you are also doing protection testing of a relay, right? First thing what you do, you insert a test block so that you can make a connection and do the testing. So similar thing is also defined in the standard edition 2 of 16.850, that you can put your device in the test mode without disconnecting anything. No need to disconnect it from the system. You can simply connect the this is the background. First I'll give you the conventional testing. So conventional testing, you are doing every single connection like wired between the test kit to the relay, analog connections, cable and everything. You are taking the feedback also in the form of wired connection. This is the conventional way of testing. What you can do in a digital substation testing, because the sample value flows on Ethernet, goose is also flows on Ethernet, right? So simply by connecting two Ethernet cable, you can do the complete testing without connecting any hardwire, copper wire connection. So this is the connection. So for example, this relay test kit has to subscribe the goose, which is published by this relay when it will sense any fault. For sensing a fault, we can inject the current and voltage in the form of sample value. So only two Ethernet connection from the test kit, and you are good to go for the testing. I was talking about the test block mode. Maybe there are two modes defined in the standard. One is simulation inductor. So you can put the device in the simulation mode. Like if you put the IED into the simulation mode, this will only subscribe the sample values and goose, or publish the goose with the simulation flag. So these are digital signals, right? Sample values and goose. You can put that signals as a simulated ones by checking it by test kit or by the other things also. So you can put the device in simulation mode, or you can also put the device in test mode when you want to do the testing. So how it works exactly? So in normal operation, ID will be, the simulation mode will be false, and the test kit, if the test kit is sending any signal by by putting the simulation flag high, this signal will be not subscribed by this IED, because the simulation mode currently it is in false state for this IED. This is normal operating condition where you are not going testing, everything is live. Now the two modes, like the test mode, again test mode is also on mode is equal to on, not on test mode exactly, and Q test is equal to false. That means this device is also not on the test mode now. This is the normal operating condition for you. But when you want to do the testing, so what you can do, first thing is that you can put this device, the simulation is equal to true. That means whenever there will be a simulated signal on the network, this device will subscribe that signal, right? So either it is sample values or goose. And you can also put the device on test mode. Test mode on, Q test is equal to true, means mode is test now. So now it is in test mode. So you don't need to take the device completely out of your connection like you used to do for analog testing, right? Conventional testing. Now you don't need to do that. Only in the relay you have to do this two setting, put the device on LPSD in true, and mode is equal to test. You are good to go for the testing, and then from the test kit you can inject the sample value with the simulation flag, and you can take a feedback of the goose with the simulation flag as a complete protection testing that you are doing it with the conventional relays nowadays. Next part, we talked about network. So there are different levels of a substation, we said, right? So one of the level is that station level. So it is forming as a network in a substation. So the network also required some kind of a testing. maybe one of the things is that you can analyze and measure the sample values and goose signals, whether it is correct or not. So for that we do have different solutions. So there is one of the devices, Danio 400, that is mainly a network performance sample value testing, those kind of a testing. You can do it with this device, and it also have a feature that it can test the network redundancy, because for network, as Yugnath also said, there are different kind of redundancies are there, right? SSR, PRP, what is implemented. So if you want to test those kind of things, again, this device is quite handy. Network, if it is a network, again we have to check the performance of the network. So how you can check the performance, like the bandwidth, definitely whenever you have created a network, you have taken some kind of a data that this much bandwidth is required to operate this substation. So if it is going beyond, maybe more bandwidth is more data is flowing on the network, because of the more data, maybe some critical things may get slow in a substation, mainly in the digital substation, right? So where you have to also check the bandwidth, you have to also check the propagation delay. So as per the standard, if I go, there is defined that from point A to point B, any signal is flowing in your digital substation, there should not be delay more than 3 milliseconds. Right? So that testing, if you want to do that for any signal from point A to point B, how much time it is taking to flow, again this device is quite handy. If you want to check your PTP synchronization, whether it is PTP correctly synchronized or not, right? What is the GPS profile of it? So again, this device is quite handy for that. Maybe quick information, like quick screenshot. So this is the time signal view. So this Danio 400 is having a feature that it can measure the analog values as well as the digital values. So directly, if you want to do the sample values in the form of sine wave or something like that, it is not possible, right? But at least for analog ones, we do have oscilloscope where we can see it. But for directly, if you want to see the sample values, the sine wave or something like that, harmonic percentage, phase angle, those things, if you wanted to see that, again the Danio 400 is quite handy. Into the time signal view, you can see all those things. It is also having one feature, that SCL verification. So we all know that nowadays more or less every substation is having a SCADA, right, where one SCL file or SCD file will be there, where the all complete substation informations are there inside of it. So what you can do, you can verify your SCL file by importing into this tool, connect this tool to your network. So whatever the information are there in your SCL file, whether the same information is available on the network or not, this will verify it. For example, some goose control block you have defined into the SCL file, but it is missing on the network exactly. For example, it is in the SCL file, but on the network implementation, it is not there, right? So it will verify it. It will give you a tick or cross match that beside that ID, that for this ID this is cross. That means there is a mismatch between the SCL file and the network data. Then network performance, this was I was talking about. So propagation delay, so from point A to point B, how much time it took a signal to reach. So it should not be more than 3 milliseconds if I go with the standard. So that checking you can do with this device. You can verify the network redundancies. So whether it is HSR, PRP, so these network redundancies are mainly in the digital substation to have a 0-second delay. So if one thing goes wrong, other thing should work. So if I take an example of PRP, so there will be always 2 paths for one signal, right? So from the both paths, same signal will flow. So even if one path goes wrong, other should be able to send the signal to the desired location. So that is PRP. HSR is mainly the ring. So even the ring breaks. So in HSR, the signal flows in 2 different directions. Same signal will flow in 2 different directions. So even one direction goes wrong, something path break, it will come from the other direction to the destination to reach it. So these are the 2 protocols mainly used in digital substation, SSR and PRP. And if you want to test that, again this device is quite handy. Other than that, SCADA is a very important. Nowadays, SAS is there in a substation, so you also have to do the testing of your SAS, right? So for that, if maybe how many of you have worked with the SCL file or SCD file? Maybe a quick hand raise. No, none of you, right? But how many of you have know about the that SLT diagram of your substation? Maybe everyone, right? That is the first information we used to go into the substation and we get to know about it. But more or less same information, not exactly same, but a lot of those kind of information is available in the SCL file also. How the system, your substation architecture, right? what are the different labels, what are the different IEDs are there. Every information is there in the SCD file and SCL file also. But to understand that, for us, we are electrical engineers, right? So understanding it is not very easy, because those SCL files were mainly used maybe by the XML coding or by the tools like Siemens has it, right? They used to make it. If you are using Siemens tool, there it is quite easy, but people are also making those SCL file, SCD file by the XML codings. So understanding XML coding for us, it is not very easy. But the tool what we have, Station Scout, so as soon as you import the SCL file or SCD file, it gives you a kind of a zero line view that we used to call it. Not exactly the SLD diagram of your substation, but the information what is there into that SCL file. As soon as you import it, it will give you the information in the voltage label. There are different voltage labels, bay label, inside the bay label, which IED is associated with which many switch gears. So those kind of information it gives you. So it gives you a very easy way of understanding the SCL file. Otherwise, understanding the SCL file for normal persons who is working in this industry from last 20 years, it becomes quite difficult, because we are mostly dealing the conventional substation. Now this SCL file, SCD file is quite taking up, right? And for even troubleshooting, so this device helps you to find it out any communications issue. Again, it also compares the SCL file, like the Dynia 400. What it does, it is also the tool that compares the information what is there on your SCL file, SCD file, the same is available on the network or not, live, right? And after the comparison, it also gives you the differences. If there are some differences, I do have some examples in the later slides. If there are some differences, it clearly tells you this is the difference, so that you can work on that difference and correct the differences what you are having it. One more thing, nowadays the engineering part you said, right? So engineering happens on the table itself. So during the engineering time itself, if you are having any missing equipment, for example, if I take an example, there are 4 ways. Now you are adding one more bay to your substation. So before adding that one more bay, physically everything available, you can simulate the missing equipment, for example the IED, into this tool, and then you can check the configuration of the SCL file, whether it is made correctly or not. So you can simulate the missing equipment, or there is a possibility that you can simulate the complete substation onto this tool, and then you can verify and check your SCL file configuration. You can create a test plan, same test plan that you have created during the FAT, same you can use it during SAT, same you can use it during the regular maintenance activities also. So in digital substation, testing is quite mandatory. If you are upgrading any firmware of any relays, it is always recommended after upgradation of the firmware, you should do the testing of your that ID. Not only testing like protection testing, testing of the test plan inside of it, for example interlock logic, right, communication testing, those kind of a testing is also required. This is an example of SCL verification. Already I briefly give you an example, explanation. You can make this device, Station Scout, as a maintenance HMI, not exactly the SCADA HMI, but maintenance HMI. Whenever you want to do some kind of a maintenance or testing, you can use this tool, and then you can do the troubleshooting. As I said, it will tell you the differences. You can do like communication testing. So for example, in this case, there is a communication issue where this IED should be subscribing or should be publishing one of the goose messages, but it is not now. It is not publishing now, right? So there is a clear indication here that the goose message appeared on the network. Okay, so there's different communication issues. So there is duplication of the goose message, right? So this is the issue. So duplication of the same message should not also be happen on the digital substation. So this is clearly giving you an indication what is that issue exactly. Then interlock testing. So for logic, some kind of interlocks are always there, like breaker opening, breaker closing, or isolator opening, isolator closing. So logics are there in the IEDs. So if you want to do the interlock testing, again this is quite handy. You can create a case scenario where first you can define which are the things first need to be get fulfilled. For example, 2 of the breakers should be closed, 1 of the isolators should be open. Then only I'll be able to make an operation of the another breaker, right? So those kind of interlock testing is possible here, and you can create a test plan, same test plan if you have tested today, next day, or day after tomorrow, or after 1 year again if you want to test the same thing. Simply you can reuse the test plan that you have created in the past. One more new feature that we have added. So mainly the communication happening inside the substation, it is on 61.50. But from outside of the substation, the other things are coming like IEEE 104 standard, right? So maybe RTU or gateway. There it is involved. So if you want to test that thing also, so you can test it. So you can actually test a signal. For example, you are changing anything with the 104 signal, and then in the substation it is converted to 61.50. You can check this end-to-end testing. So you can change any signal in the from 104, and then you can verify whether the 61.50 signal got changed or not. It's other way around also. You can do the changing with 61.50 signal, and then you can also verify the 104 signal whether it is got changed or not. So this end-to-end testing feature we have recently added. So if you wanted to know anything in detail, we do have a stall. Maybe tomorrow we can discuss about it in detail. But because of the time shortage, I cannot talk about in detail. And cyber security also, Yugnath has given emphasis on the cyber security. So digital substation and even the normal SCADA substation, the substation nowadays we are having it. Cyber security plays a very important role. So we do have the solution for that also. We call it a station guard. It's kind of an IDS solution, intrusion detection system, where we provide a lot of facilities. Like first is the visibility. So it gives you the any cyber risk. If there are any cyber risk is there as per the configuration of your substation, this will highlight you. It will give you an asset inventory also. So maybe 20, 30, 40 numbers of IDs you are having it. So you can create your asset inventory. Using that asset inventory, there is one more term in cyber security, that is vulnerability management. So if I take an example of the Siemens relay, if maybe some relay where there is a risk through which it can be used as a cyber threat, right? So what Siemens will do for that, Siemens check it, Siemens publish a score on the website that we call it a CVE score, and according to that CVE score, it is calculated that how severe that threat is. So that is what it is called, vulnerability management. So if any vulnerabilities are there with this device, Siemens' responsibility is that they will publish it on the website, and what we do, we show that data to you that these are the IDs are available, these are all correct. Maybe with some ID the vulnerability is matching, that means there is some issue with that, and Siemens also will give you the information that what is the solution of that. So they will definitely give you maybe a firmware upgrade, you have to do that, right? So that information you can directly get it here on our dashboard. For this ID you have to upgrade the firmware, then you can get rid of this cyber risk, right? Then intrusion detection already informed you. Maybe for how intrusion detection works. So intrusion detection works in the philosophy that first you have to set some rules for cyber security. So for all the IDs or substation, you have set already the rules, you have created the baseline. Apart from baseline, if something is happening, right? Maybe you have already defined there should be only 10 PCs. That's not, if any another PC connected to your network, this will directly give you a alarm on your substation that there is something extra connected, right? So something happening beyond the rules. It is just an example of the PC, but it could be the behavior of the ID also. So the ID definitely for the whatever the purpose it is connected in a substation, it is behaving like that. But if it is behaving something fishy, right? Maybe cyber because of the hacker, he did something and he wanted to do some fishy things, it will give you a alarm on our dashboard that there is something abnormal happening, right? So then you can take a call to avoid this kind of a thing. Then functional monitoring, this is very means kind of unique feature for us, functional monitoring. So if any communication or configuration errors are also there, that will be highlighted into this tool. Okay, so next is the main, because we have the demo setup here also. Okay, so we'll break for now, and after the lunch we're going to have this small presentation of this merging unit testing, because now earlier CTVT, transformer, breakers, those are also an asset for you to do the testing. But if merging unit is also the part of your substation now, this is also one of the assets that you have to do the testing and verify whether it is working perfectly or not. So that's why we have the setup here to show you the merging unit testing. Maybe after the lunch we will going to show you the testing part.
function will start at 1:30.
Yeah, till now if you have any question, because we have 7 minutes at least, so we can take questions. Yeah.
So wildlife function will start at 1:30. So be back by 1:30. Finishing.
Values, the testing interlocked, a lot of things are there, right? So if you have any questions, you can ask. Okay. Then we'll break and then we'll meet at one.
Merging unit interlocks can be set with the merging units.
Interlocks into the merging unit, maybe Siemens can comment on it.
What's that?
Interlocks.
Yeah, it can able to handle.
Okay.
There is generally PCU used in the substation, but Siemens merge you can able to handle interlocks as well as controlling the breakers also. PCU as fast as that PCU saying that you can test like the box. How you can access that PCU?
one more, right? Aman,
ಬ್ಯಾಟ್ರಿ
mic.
ಅಲ್ಲ ಮೈಕ್ ಉಂಟು.
Yeah. So, good afternoon, welcome back, and I'll try to make sure that nobody's sleeping. Okay, just kind of glance or maybe kind of recollection. So, the one which we are representing here, it is Siemens merging unit and relay. And maybe like let's assume like in a conventional substation, suppose for example if you want to perform a relay testing, so straight away you can take one relay, maybe, and you can take one relay testing, directly you can able to inject current and voltage. But if it is digital substation, maybe like from the morning from Yoganath and like Mani Singh, so we were telling that it is all like through sample values, it all like goes through the fiber optic cable. So how will be performing those kind of testings? And when it comes to fiber optic cable, you have to inject the sample values. There are some standards, 61850 9-2 LE. It says like you have to inject 4000 samples per second, and you have to maintain that 4000 samples per second. And it should be like continuous along with time synchronization. Because when it comes to conventional substation, whatever the current and voltage, right, it goes in light speed. If it is a digital substation, it's all like not light speed. So there the timestamp matters a lot. So it will timestamp and it makes sure that it is reaching to a relay from merging into the relay in a proper timing and with proper timestampings. If a sample missed out, a protection function doesn't work. So this is the basic concept. The first criteria when it comes to digital substation, you have to make sure that your merging unit is working fine.
Is there any case of missing samples? This is a redundant network.
Actually, sir, suppose when it comes to like protection, it's full of backup, and digital substation also the same backup schemes has been created. Redundancy. You would be having 2 GPS. You would be having a scheme called HSR and PRP. 2 LAN port would be there.
Either PRP or HSR.
Yeah, HSR or PRP. So it's a nice question. You would be having HSR or PRP. Even one side, if it just fall down, maybe like some issues in the relay, or maybe a relay is getting switched off, or maybe your switch is getting switched off, it should reach the, with no time delay, it should reach the particular maybe like protection function, or maybe a sample values or boost should reach in the other direction. So that is what the scheme is. But when it comes to testing part, the first criteria would be like your merging unit, because once it is going to get digitalized, right, from the merging unit only it is going to get digitalized. Okay, from conventional to digital it is going to get changed over there. So let's see like what aspect it would be. First, when it comes to digital merging unit, there is a standard actually. The standard says 61869-30, and in that standard it specifically mentioned like how to perform merging unit, because that is the first part which you need to take care if it is a digital substation. And the standard talks about merging unit testing mainly, and what type of accuracy you have to perform. Suppose for example for CT, right, we will be having 0.1 class. For checking 0.1 class, maybe like if it is a meter, maybe like energy meter or something, so if it is 0.1 class or 0.2 class, you should have better accuracy of 5 times to perform that calibration test or testing of meter. Similarly for merging unit, in this standard, it is specifically mentioned about like how to perform the test before you get the instrument from the manufacturer at the factory. Once it is reached your venue, how to test. Once it is connected with the grid completely, how to perform the test. So all the test procedure has been mentioned in this standard. So what we are going to do it here, the same thing we are going to cover it here as per the standard. So first, this particular picture has been taken from the standard. So you can see here, there is a, okay, so you can see in the first actually 9-2 LE analyzer, then you'd be having a DUT which is nothing but merging unit which is placed here in between, and there is a current and voltage signal generator, which means you have to inject, the dotted line is nothing but analog values. What standard says, you have to inject the analog value to the DUT, which is nothing but your merging unit, and the DUT will produce the sample values. So what you have to do, along with the time synchronization, you should capture the sample values which is producing by the DUT and the analog value, because from analog to digital it is getting changed, and you have to take both and you have to compare and you have to check it up the ratio error, phase angle error, any drift in the merging unit. So this all the test you have to perform by this particular Its standard has been mentioned. Okay, PPS, which I mentioned, which is nothing but in the very old, maybe like in the edition 1, PPS is the time synchronization, pulse per second. But when it comes to edition 2, it is all like more fast and it should be common. That is called Ethernet. So Ethernet will get complied by PTP, which is nothing but precision time protocol. So that's what in addition to it is mostly like PTP, and it is also simple. If it is PPS, right, you will be always having like one particular port, BNC port or those kind of port, and that you cannot arrive at every place. So that's the reason things have been moved to addition 2, which is PTP. So what we are going to do? So we are going to we have a relay test kit. From there you can see V and I. Analog will be injecting, and that particular DUT merging unit which we have Siemens here, so that will produce the sample values. SV is nothing but sample values. That will be capturing with the help of product called Danio. Maybe like in the past what happened for performing merging unit testing or maybe like network testing, we have a product called Danio. So now like we had come up with a new product called CMC 500. It's a relay test kit. Now the same relay test kit is capable enough to measure the sample values also. So now what we are doing, like instead of Danio, what we have done, we had replaced with a new product called CMC 500. So you can see this is the exact scenario here. So we have CMC 500 that will inject the sample analog values, that will also measure the sample values. You don't require one more instrument to measure the sample values. So this is what we have done, and with this, right, again, like we will see like how we are performing it, testing and all. I'll show you like how we are performing it. At least now it is you're getting some idea like what we are going to do with the help of this setup. So we have relay test kit, merging unit will be injecting analog value, merging unit will be giving a sample values that we are going to compare, and we have to check it up the drift, accuracy, those things we are going to check it up as a kind of first phase.
Time drift and accuracy. Time drift and accuracy.
Yeah, because this is a GPS actually. So using this, right, we are also make sure that time synchronization is possible. And as Yoganath conveyed, right, by chance if the GPS is not available, automatically it will start produce it will act like a master clock.
That master clock functionality is there.
Is there.
So without GPS also can we perform this testing?
Yeah, perform. We can.
So what is the reliance on GPS clock?
No, GPS is required to, the SMVs has to transfer from merging unit to the protection device. It should be time stamped. So both the device should be synchronized, time synchronized. Not only the transfer from SMVs from merging units to the relays will be accurate.
So how much days or which your clock can maintain the synchronization? What is
how much?
This grandmaster clock after losing a reference source, for how much period he can maintain?
No, it is a continuous process.
Continuous.
Continuous process.
There will not be any time limit.
No.
So without the GPS clock, can you operate this?
Yes. But only thing, it should be maybe it will be synchronized with this time.
Time may change. So even timing may change your test.
Sir, no, you can make it simple that they should be in the substation time and everything. And one thing would be right, if it is different time, other devices are different time, right?
So PTP process it is done, sir. Sorry,
the time may drift.
Time may drift.
But it will maintain the clock.
But if we assume that this is having different time and another ID is different time, so.
No, if one is acting as a grandmaster.
No, that is only for the SMV transfers, not for the general time. If the fault is happened, between two bays, that time will be different.
So no, if it is acting like a grandmaster clock, it will send the time to other slave clocks.
Slave clocks.
So it will stamp
between the merging unit and the device only.
Okay, first we will do with the GPS.
Yeah.
Then we will remove and see what is happening.
But internally they have to make it actually. But still, first we will perform the testing, then we will do that. Okay. So
Sample why you are taking back to the kit again feedback?
I think you missed this slide, I guess. I'll show you this slide. For this particular reason only. This is a standard actually. The standard as mentioned, you should measure the analog value which merging unit is getting, and merging unit is converting analog to digital. That also you take, and you should see the difference now between sample values and analog values.
So the kit is produce SV?
I am not producing SV. I am injecting only the analog value in the merging unit. Merging unit is producing SV. I am measuring the SV through Ethernet kit.
So kit has the
Yeah, it can also generate. But now at the moment our priority is to perform only this particular testing, merging unit testing. Even my instrument can able to generate 4 sample values. 4 means 16 current and 16 voltage it can able to generate. But at the moment our priority is to perform only merging unit testing. So we are sending analog and measuring the digital. That's it. Yeah. So just before that. Okay. So it is actually connected. We made all the setup. Maybe I'll tell you like what kind of setup we have made. From here we just connected 3 current and 3 voltage to the merging unit, and from merging unit, like in the back side we have a FO cable which will give the sample values. That FO cable, right, we connected to the instrument back in the one of the Ethernet port so that it can able to measure the sample values. So this is what the connection we made here. But in the substation side, this is not something like in substation, right? Your merging unit would be in the kiosk somewhere actually, and your relay panel would be somewhere in the control room. So in that case, right, even in live, you can do the live merging unit testing also. You can just take a clamp, put it in the back side of your merging unit. It can capture the current. It can also take the voltages also, and automatically just would be having a switch somewhere in the SC itself. Just connect and measure the sample values. There itself you can test lively also. But here, since we could not able to make that setup, we just made a merging unit and relay. So what we are doing now, the CT ratio of the merging unit is 1000 amps and it is 400 kV system. That is what the configuration has been made for this particular system. So we are injecting 240 kV, maybe 230.9 kV, which is phase to neutral, and 1000 amps. So this is what we are injecting. If it is sample values, there is no secondary, it is full of primary. Okay. So we are injecting in terms of primary. Once it is injected, you can see there will be an option. This is the measuring tool actually. In the same software we have, so you can see there is options: analog voltage, SV voltage, and SV current. So analog means whatever I am injecting, and SV is nothing but whatever I am receiving. Okay. So this two I need to first of all capture, and I need to understand like what is the current and voltage it is measuring. I know very well it is 230.9 kV I am injecting and 1000 amps I am injecting on analog. So digital, now we want to verify like how much it has been measured. So you can see on the other side, other direction. Yeah. So you can see here 230.96 is the voltage which we injected through analog. On the digital side, SV voltage 230.63. And if I come up upper side, you can see here the current. This is analog current, 1 kiloamps we are injecting. The measuring is this much. And automatically, right, it will see the accuracy. So the drift is almost like 10 amps or 5 amps. If you do the calculation, it will be below 0.05%. Maybe that is what the measuring unit accuracy would be actually. And most importantly, what you have to do, you can see the error percentage here, 0.1, 0.14 for the voltage and current.
So this you are converting into secondary injecting.
Yeah, actually my merging unit has to understand in terms of primary only.
No, you are injecting analog value.
Yeah, secondary values only I am injecting.
But you have given primary value.
Yeah, actually there is an option.
That is just a scale, sir.
Yeah, there is an option, like you can go to view, you can set as primary, put the CTPD ratio. So the understanding would be like in terms of primary. Okay. You can see the phasor view actually. This is for analog. Then you can see there is a digital. Just capture. Just capture and leave it on the. So you can have a live view actually. I just captured and I just put two different. One is analog and digital. You can see the differences and everything you can able to check it up. And you can see how much voltage is measuring. So 239.96. Since it is analog, right, it is constant. If it is digital, right, it is just fluctuating. You can see the differences. And simply like you can put the two waveform together and you can check it up what kind of accuracy in terms of percentage, what kind of drift, whether it is current, voltage, so everything you can able to check it up in a live view. Suppose for example, you have a merging unit where you want to check it up 5 times of current and 10 times of current, you can inject 10 times of current and you can check it at the accuracy of the merging unit. Because this is all like mentioned in the standard, like you have to mandatorily perform the merging unit test first as per the standard along with the time synchronization, then the normal protection testing is required. Yeah, we have to actually set a reference, maybe like the GPS, maybe the time synchronization could be the issue. If the time synchronization is an issue, right, because this is a kind of setup, both the relay should be in together, both merging unit and relay should be together. If I just bypass merging unit, so I bypass the relay and I just injecting only on the merging unit, so it is also searching for the clock.
The clock is already you have given, na?
But I didn't connect it to the relay, I just connected to my instrument only.
Now it is a grandmaster's enabled, sorry.
Yeah.
Built in.
So there is a drift in the phase angle.
No, that is what actually, this actually need to be connected to the relay. Basically like the setup has been made as a digital substation
So
setup.
if grandmaster clock is enabled, how that shifting is coming?
No sir, he is break the loop.
No. Now there is, have you enabled the grandmaster clock mode?
It is there,
Enabled, but the phase shifting is coming.
And the time reference should be there, no?
Sorry sir?
Time reference is available now.
The phase angle is varying.
Phase angle between the voltage and current, right?
No, actually between analog and digital.
That is what there is actually correct another number. Like we are just doing only merging unit. Because this one is given a master clock, right?
Because it is disconnected with the protection device, sir. Now we are testing only the merging units.
I agreed, but the merging is having grandmaster clock, right?
No.
Relay is having the grandmaster.
Merging unit not having.
Merging unit, relay is having the grandmaster.
So have you enabled the grandmaster in relay?
In the device, in the relay.
Relay it is enabled.
Relay it is enabled.
Once grandmaster is enabled, that thing will sync with this grandmaster.
So these two will sync. Relay kit cannot sync.
Okay. No, kit why it cannot sync? You have set the IP address of the grandmaster.
No sir, that is, see, it is not like a normal time sync, sir. Only relay and merging unit can synchronized. So if we can test with this, if we can test, because he bypassed the relay. He bypassed the relay, he just injected the analog values and measured the digital values. So it is not, the merging unit is not getting any reference now.
Narayana, this GPS clock where you have connected?
This is my GPS I just connected here.
So this kit, can it give any reference to the relay?
Yeah, it can give to the relay, but provider actually, like all this, right, it should connect it to a switch.
That complete setup has to build up.
Complete setup has to, because this also should receive the time sync, this also should receive the time sync. The one I am injecting, that also like it will inject along with the same time sync. So all three should see the same thing, then only it will get synchronized.
So you don't have you should have to, in a circuit also there were two lines, right? One should go this way, the other should.
Yeah.
Here you have only one connection.
Sorry,
the clock.
Yeah, no, ma'am. In the clock would be actually only one. So that can be like
there in your figure also, the earlier figure that you showed the connection should go to both. Correct?
Yeah, that's what it should go to both. Yes. Yeah, true. It should go to both actually. Yeah.
Sir, that testing will come to know when you test both. He will inject the current in merging unit.
That we will perform actually.
And will
along
measure
with the relay will perform.
There we can compare it. Because now we have disconnect from the source.
Now it's given to the kit only, time reference.
So first of all, to activate this, right, you have to keep it outside.
Yes.
Then only, here actually we thought of simulating something to show you actually. To get the GPS right, you have to keep it in 360-degree outside. Then only it can able to take the satellite and it will do the time synchronization. Since it is having a master clock, right, for the protection testing we thought of using that master clock.
See, okay, can you check the status of the GPS?
This one? Sir, it won't receive any satellites.
No, can you check whether it is receiving any satellites?
Well, actually what happened, there are two options actually. You can see it is not logged. First of all, it should get logged. number of satellites, it is receiving 0. By chance, if you go outside, right, it will start receiving the satellites and it will get the time synchronization.
So this is a unit which is to be placed outside.
Yeah, then only it will
able to
get
connect
time.
to the satellites.
That's right. Sir, in fact, what we will do, we have a common receivers. We will make a loop and we will connect through switch, so that all are synchronized.
This one is actually used for end-to-end function.
Which one? You can use for end-to-end testing, you can use for digital substation testing, all the purpose you can use.
It's a multi-purpose.
Waveform spikes. How exactly it behaves? Because earlier that is not the case. Directly, like you'd be having a CT secondary would have connected to the relay. But now we have a merging unit which is in place. It will take all the currents. Then it will give it to the, it will convert and it will give it to the relay. So you have to do that calculation. So that is what has been mentioned in the standard. So what you have to do using this kit, or maybe like we have a product called Danio. You can inject and you have to make sure that you're capturing the sample values without any spike for maximum fault currents, short circuit currents. Those things we have to do it. And this is the standard like which you have to repeat it for 3 times. And you have to make sure that not even one single sample is missed. If the sample is missed means you will be losing some like important trips. If any trip comes, it doesn't give any trips or not. So you have to repeat this particular process. So likewise you can see here for 50 Hz like 80 samples, for 60 Hz it would be like 80 again 80 samples. It will get changed actually. And 250 samples, 56 samples it is mainly made for metering and power quality application. So the same thing you have to process it and you have to check it out. So now you have an instrument where you can inject the analog value as well as you can measure the sample values and you can do the same calculations, which is possible. Similarly, this is for power quality measurements. The same thing, again you have to inject for 1 minute, repeat it for 3 times, make sure that you are not missing any samples. So this is a kind of test procedures which you need to follow for merging unit. Now I'll just like you made the connection. Okay, so now we just made the connections. What we have done actually, the main relay, right, which will now it will give a time synchronization to the merging unit. So maybe like I would request you can go and you can check it up. If it comes right properly, there will be an option called failure will go and it will start gives the measurements. So now what we'll do like we'll, with the help of our relay test kit, we'll be injecting a current and voltage to the merging unit. Merging unit will change the values in terms of digital. Now it will give it to the relay, which is a protection relay, line differential 786, and in that we are going to perform a protection functions.
So now it is showing 0, no?
Now we will inject, it will measure.
Now if the communication is interrupted, it will show as a failure. The communication is established between these two merging units and the protection device in terms of all, including time sync and everything.
Dixie, have you stopped the production of 356? Still there?
Just make it clear, sir. No, sir, we have not stopped the production of 356. Still, 356 would be available for supply till 2026 December. After that, we are going for stop. Whenever we stop, we have a company policy. Only we have, I think so. From there, we used to support for next 10 years, which means you have a complete service support, software support till 2036 December 31st. It will be available. So any product we stop, we will supply for 10 years. And going, this is a future, maybe I'll tell you some of the important functionalities which could be like more useful. I'll just show you about that. So just give some trip and make sure that it's working fine. In the meantime, I'll just trip. Yeah. Then distance trip. Yeah. Just place some faults and check. You open this one. Distance. Thank you. I'll also keep it ready. Okay, actually they are making the setup actually. In the meantime, I'll just finish my slides. So first, now only like I'm coming to the topic which we requested. The topic is exploring emerging trends and breakthroughs in testing and diagnostics methodologies for power grids. Because like in the morning, Yoganath has conveyed, right? Things are like moving really forward in terms of IoT, cloud, digital substation, digitization actually. Things are actually moving really fast. And with that, right, we also like being a solution provider, we should also have some sort of solution. So that part only we wanted to cover. So first, like we talk about some of the challenges which is going on. These are the present challenges which we used to hear from the customers when it comes to conventional testing or whatever it is. These are the present challenges actually. First, maybe like over it is any electricity board, we used to hear this particular term. One is outage period would be really less. In that given period, you have to perform the testing in all aspects. And second is like during that particular period, you have to perform a very complex schemes. Maybe like simple overcurrent and all you can able to perform in a very simpler manner. Whereas if it is a busbar testing or maybe like let's assume end-to-end testing, line differential, you have to like make the setup in two different substation, inject the stability, check like distance also if possible, and again the given period would be really less. And nowadays the relays, right? I don't want to like put anybody down, but relays, it's becoming very smart. Maybe 50-40 years back, it is very simple, one pickup current, one time. But now a relay is having like more smarter, and everything deals in the algorithm. Some of the things, right, it deals with the algorithm. So what we actually like recommend, we should also go to that particular level to perform that algorithm based testings, scheme based testings, because nowadays it's purely communication. Here like it'd be having like in one panel 15 electromechanical relays. Now one relay will do like 10 panels job. For that algorithms is there in the picture. So we have to start perform the testing with respect to like scheme based testing or some transient behaviors. Because relay always thinks on the live fault scenarios, but whatever the tests we perform, keeping current as a constant, varying the voltage, no. In the live case, that's not the situation. So we have to deal with the same transient behaviors. We have to like recreate the mal operations. So those things, like we have to do it. That is something like the challenges which we are seeing in the conventional system. And these are the main testing challenges. The workload has been increased a lot. The time has been like given very less. The outage period will be really less for everyone. And the repetitive work. I'm sure like the same engineer, they'll be going to perform whether it is a transformer or relay or CT or PT. The same assets, they'll be like year and year they'll be performing it. The repetition of work could be more. And documentation and information exchange. Because the same engineer is not available for the same plant. Maybe like different transfers and everything. And again the information which the person who had, right, it is going with him. The new guy who got replaced, right, again he has to start from the scratch. So these are the kind of hurdles. Okay, so for that like we have solution. Not only now, actually for past 20 years we were having a solutions called test automation. Suppose for example I'm just entering to a substation, I'm performing relay testing. You just test whatever the observation you made, capture and you can put it. You can type. Suppose for example while testing in the panel, I found like one particular TV was broken, I made in different way of connection. You just capture and document it and circulate the file within yourself. It is something like one-time investment. Whenever you go and perform one particular protection, create the test procedure, make sure that you are just repeating it for different relay manufacturers. Only thing is that you have to go with the test procedures. So that is what like we actually recommend, because in the modernized days, like this is really important. And how exactly it should be, because the goal should be like the minimum clicking. I can give you an example. Suppose if you are using maybe like testing a distance protection, don't think about my relays, relay test kit. Think about any relay test kit manufacturers. You'll be opening quick CMC, doing the measurement check, then you'll come back, you'll open the distance module, perform the distance testing, then again you'll close, then you'll open overcurrent module, distance maybe like you'll be opening different modules. So this is for one time. Assume the same relay has to be tested twice in a year or maybe like for next 20 years. So how many times you are going to do the same job? So for which actually like our idea is that if you are using a tool which is actually available for free of cost, Omicron Control Center or our libraries, we are well known for libraries.
Omicron Control it's not free.
Maybe like 6 years back it is chargeable basis. Nowadays we are giving free of cost to like encourage it.
Control center?
Yeah.
You can install it?
Before 6 years, maybe after 6 years, like maybe 2018 onwards, whoever purchase it will be free of cost.
For older machines, it will be still licensed.
Yeah, because like we wanted to encourage that, let them like use the real benefits. Because the ultimate idea is that suppose you are going to a substation, you are going to perform a testing. So what you can do, you can go and automate it, because KSEB would be having their own test procedure. Just it's a one-time investment for one production function. Distance, differential, generator, feeder protection. Just create one good OCC as per your test procedure. Then come with the test procedure. If you are going with different relay manufacturer, different model, just import the settings, start performing your testing. Instead of like every time going to a substation, opening different modules, it's a time-taking process. And again, like you'll be having one report. And further, like what we have done for further our enhancement. If you have one panel, one OCC. If you follow this particular rule, right, control center with our testing library and with the help of link to X-ray, right, you can completely automate one panel. And the best example would be like nowadays, some of the electricity boards, they started following it. They'll go with their OCC to FAT or commissioning, they'll use it and they'll come back. And it will be like, your time will also get saved. The person who is doing the testing for you at FAT or maybe SAT, their time will also get saved. Okay, but the amount of uses are very less, sir. Because now, like we are talking about automation and everything, still we are seeing that, people are familiar with quick CMC, advanced distance only. But if you can able to put all the modules in one particular location, right, it is really good. So that you can able to do it. And second, this is what something kind of graph actually. You can, I'm sure like you know about our software modules, quick CMC. When you start use quick CMC, right, the individual modules, the amount of, like time, it will be always on the higher side. Once you like incorporate the PTL, your OCC, your test procedure, right, the really like automation would be more and the time which you are spending at the field would be really less. And now I tell you one step we went forward, and what we have done, nowadays we are giving for each and every template the procedures also. So you can open the templates, you can fine tune for your own test procedures. It is not something like you have to start from the scratch. For each and every relay, we are giving the test procedures. That is also available. And this is how it looks like. Suppose if you would have made your own test procedure, you can see here, one is like wiring test, then it would be like stability, then slope, harmonics, backup overcurrent, overflux. So it's one particular test procedure. Happily you can go to the top, just one click, start all. Once it is started, right, take a tea or coffee and enjoy the test results. And the same template, next time you can use some different makes or model actually, just remove that particular, add that particular make of relay, import the settings, start performing your test. And this is another thing. Suppose for example you have a relay. In your relay, like you'll be having different elements. Overcurrent, earth fault, distance. So the condition would be like, if your distance gate fails, your overcurrent has to come into the picture as a backup. If the entire relay is failed, you would be having another backup. So it's full of backup. But whenever we perform a normal way of testing, to achieve overcurrent, I have to disable the distance protection. So this disabling and enabling should be always would be there. So that's the reason, like what we had come up with a solution called scheme-based testing. So if any functions, protection functions, or maybe like teleprotection, your bus scheme, or maybe like your end-to-end testing scheme, any schemes, or maybe like I told you right in the beginning of the presentation. Nowadays, like some of the protection functions are algorithm based. Let's take an example. If you have maybe like there is a protection which has been implemented by Siemens called sympathetic inrush. Sympathetic inrush is nothing but you have parallel two transformers. One transformer they have taken a shutdown, and when they put the transformer in normal position, some inrush will play in the transformer which is in live condition. So that particular time that relay should not initiate the trip. So that is called sympathetic inrush. So that particular feature has been implemented by Siemens, but if you want to perform that, it is not possible because it is algorithm based. Similarly, we used to always talk about CT saturation, but how many times we saturated a CT and we have seen like how the relay behaved. So those kind of toughest thing or maybe like scheme oriented testing can be done with the help of a software called relay sim test. So that's what I'm going to talk about. So why scheme based testing should be part of your production testing? This is actually a study where you can see which is in the gray indication. This 12% of AC system failure or maybe some personal error or DC system failure. This is all like not in our control. Being a production engineer, you can see parameter based testing, 20% protection device malfunction. So whatever the testing we are performing at the moment, like by injecting the current and voltage, varying the current. So these are like you can able to spot out some 20% of malfunctions. And as I told like in the beginning, nowadays a system is nothing but full of communication. Whether it is end-to-end testing or teleprotection, even if you have bus bar, you will be having some sort of schemes with help of communication. So with help of scheme-based testing, where you can able to spot almost like 65% of errors which is happening in terms of mal operation. Maybe like sometimes we heard from the customer there is a zone 1 fault, but zone 1 is not tripped, where backup power current is tripped, and there is maybe like evolving fault, zone 1 is tripped for maybe like out zone. So lot of such kind of situation, right? That and all you can recreate and you can check it out. In those scenarios, right, the polarity would have kept wrong. So whenever like you are performing such kind of scheme-based testing, you will come to a conclusion that your system is fine, working fine. So that's what this is. A study has been like released by ERO actually, and what they claimed, if you can able to do like system-based or scheme-based testing, you could able to like at the moment you could able to understand your protection system better, and you can able to like recreate the settings coordinations. All those kind of things can be taken care with the help of this study. So first, when it comes to like our instrument, we have software called relay sim test, and this relay sim test, right, we are not bothered about any relay settings. Ultimately, like all the relay settings has been derived from the raw parameter. Raw parameter means, suppose for example, if it is distance from the conductor, your line impedance, from there only like whether it is 80% or 120 or 150, that has been segregated. So our idea is that just get the raw parameters. If it is line impedance, get the line impedance. If you are going to test transformer, nameplate details is the raw parameters. So only we need the raw parameter, model your own system, or else we have an existing system also. Just you have to put the CTPT ratio, model your system, place the fault wherever you want. You can place on the bus side, make sure that my line differential is not tripping because it's outzone fault. Saturate the CT and check it up how the slope 2 is behaved. Whether slope 2 has been taken care or else not. So likewise, all the realistic situations you can able to play, and you can make sure that how exactly the protection function is operating. And these are the schemes like we are taking care, means almost like all except generator protection. Any protection functions, any schemes, bus bar, on and off breaker, double bus bar breaker, anything like we can able to take care. And this is maybe like whenever we perform scheme-based testing, specifically in India, we used to like find some of the issues in the end-to-end testing settings or maybe like protection settings. This is a typical one which we performed recently. A particular EB, actually they were having a transmission line, and after some time they will be having a cable, and we performed a fault on exactly on the cable area. It was going for the auto recloser, where it should go for the lockout, because on cable it should be a permanent fault, it's not a transient fault. So likewise, whenever we perform any scheme testing on the existing system, we could able to see the CT mismatch factor. Some issues would be the time coordination, settings coordination, logics was not properly set. So likewise, we used to find it out. So that's what we always recommend, that if you perform your regular testing plus scheme-based testing at the time of commissioning time, you can you can resolve a lot of your setting issues and everything, you can able to resolve it. Okay, I just conveyed, right? You have to just take any of the template, put your line impedance, your cable impedance, place the fault wherever you want. Maybe you can place a fault on this bus, make sure that it is not tripping or reverse zone is coming. So likewise, you can model any of your system and you can able to check it out. So in this case, like we made a fault on transformer. Usually like when it comes to RF protection, I've seen like people used to inject 10 milliamps, 12 milliamps, but RF is nothing but, usually it is a protection which will be taken care of the unprotected winding in the transformer. So what you can do here, you can set a percentage. You can set a percentage after creating a fault. Maybe like the unprotected winding would be 5% or 4%. Till 96% your differential has to come. Then 97% RF has to come. So likewise you can do the realistic situation because we have the transformer data. Based on the transformer data we are creating the fault. So likewise you can check it out. So now I'll come to the important part, CMC 500, which we are displaying here. First let me convey some of the message. I'm sure most of them knows about Omicron. So we are pioneering protection testing system. Maybe in the previous instrument 356 which got launched in the year 2008 or 256 256 plus which got launched in the year 2007. Maybe you may be asking question why you had come up for one more instrument, because that got launched in the year 2007 and 8, and that particular time we got lot of appreciation from all the customers. Such a portable instrument, nobody is having very such portable. But the same customers, believe me, they were telling that it's bulky. We need some more portable instrument. So that's the reason one is portability, and second is things are moving fast towards 650, and 356 will give lot of 650 application. But provided things are maybe whatever we had come up with, maybe after 5-10 years, right? There are some technology which will boom and which has been adopted by all the electricity board that has been adopted here in this instrument. And purely this instrument has been developed basis on the feedbacks. I'll go through it. What is 6250? We implemented a very good features. I'll just cover it that. And cyber security. Maybe I can proudly mention that this is the first cyber security product in the world. You may be asking okay, relays I understand, but why relay testing?
They have started.
Okay, relays maybe cyber security I understood, but why relay testing? That's what the question, right? Nowadays, all the manufacturers or maybe all the electricity board, they are moving towards remote testing. They are moving towards network based testing. If you are implementing digital substation, this instrument will be always connected in the network. Of course, yes, maybe the relay may be secured, your substation may be secured. Using my instrument, I can give the trip, right? It's all digital now. So that's the reason this is the first cyber secure product where we want to take care ourselves. Using us, nobody should harm the substation. First cyber secure product, and safe. Earlier, we were having safe, but here we enhance the many safety features. One is for the human and another for the machine. Because sometimes we got a feedback that if you're working on a live panel, sometimes you will get some statics. Little drips and all you will be getting it. So now we had implemented a feature. Once your testing has been done, just press safe mode so that it will discharge all the statics. And second, for the machine actually, whenever you are doing any injection or something, right? It will not do the unnecessary things. Suppose for example, you have a power supply which is fluctuating a lot, right? Earlier you have to see and you have to switch off. But now I'll take care myself. I'll isolate myself. I'll safeguard my instrument. Because this is what the feedback we received. Your instrument is costly. If anything goes wrong, right, the charges also would be more. So what we have done, anything you had done from your side for the power supply, or maybe now also you can notice if the ground is not proper, I'll keep on blink. Our suggestion is that put your power socket, see the instrument for few seconds, it will tell you what are the issues on your power supply. Even after, if you are continuing, on your own risk you are continuing. And if there is a heavy surge comes, I will isolate myself. So likewise, some of the safety features has been kept for instrument also. Okay. These are the overviews actually. So this is the safety part. This is entirely a safety part. We have two beautiful features when it comes to safety. Again, some customers say I'll be breaking for a lunch. I'm keeping the instrument in the place. I have a doubt that somebody will use the instrument because in the past it is possible. You can see there is a dongle has been kept here. If you take the dongle, right, nobody can do anything. When you're breaking for a lunch, you're leaving the instrument in one place and you're going to your hotel or somewhere, take the dongle and you go. Nobody can harm anything. And again, the next question would be, if I lost the dongle, what will happen? We used to provide one spare, and that dongle is common for all the CMC 500. Okay. And another, you can see there is a small button we kept. This button is nothing but, now we introduced the new features in this particular product. You can do primary injection also for 450 amps. Just portable instrument, 12 to 14 kgs, you can do primary injection also. So to take care of that, we have kept this safe mode and active mode. Only you can able to do the injection in active mode. In safe mode you cannot do. In safe mode you can do only the connections. And you can see the Ethernet ports. The communication we had given 3 options. We are giving Ethernet port communication, USB port communication and wireless communication. All 3 communications are possible. And most importantly, we are complying the standard cyber security, right? So what standard IEC 62443 says, right, you should also give a provision for enabling the password. So you can enable the password. Believe me, once you enable the password, right, apart from you, nobody can use this product. And most importantly, as per the cyber security rules, you have to renew the password. Every 8 days, you have to keep on renewing the password. Yeah, that's what the standard says. And if you want, you can disable it also. That possibility is there. But level 1 protection is that as a cyber security concern, we used to take care of the product. But as a level 2, still you feel that more threats are there for the instrument, then you can enable the password. Okay, so those all the facilities are available. And most importantly, in 356 or 256 plus, you don't have any LED indication which current is injecting, which voltage is injecting. Here, full of LED indications. Even if the ground is not proper, it will blink. Even if it is a surge voltage, it will blink. So anything, it will blink and it will give you indications. Okay, and most important, you can see here, I'm just highlighting here. So earlier, like sometimes customer asks that whether you can able to do some 200 amps or 150 amps, which is not possible in 356. The reason, like we were having a small neutral, because all the current, phase current will sum up and it will flow to the neutral. That was not capable enough that time, because that time we didn't add such kind of idea. So now we had come up with a big neutral. That's the reason we are claiming that you can go up to 450 amps. And most importantly, here what we have done, the voltage source which we have, right, that can be convertible as a current source. Mostly, like in the industry, this is what the feedback we received. If it is convertible, right, you won't be having a, not more than 5 amps or 3 amps. Believe me, once you convert, you can able to inject 15 amps continuous, 30 amps for shorter duration, so that you can able to test any protection functions. And in CMC 500, we don't want to restrict ourselves, because in when we develop 356, there are some requests. You please give me 6 voltage source, and you please give me 10 current source. So what we have done, we had come up with 5 different variants. Suppose if you have a requirement for 6 voltage and the same instrument you want 10 current, then this is the one. This particular version, right, it will also inject 7 voltage, and it is also having a facility for 10 current source. And if you want I current module, this 4 voltage and 10 current. Likewise, many options are there. You can pick, depends upon your application. If you are happy with 7 current or 6 current, stay with it, like 356. If you want to like go for 10 current or 6 voltage or 7 voltage, we have specific versions. So now the idea is that one model, you can do everything. And this is templates actually. Most of the utilities are like having these templates with them. You just name it, we have it. Like any templates, will be having it. And today also, now also we are performing that particular testing using template only. And this is that cyber security part which I conveyed. Mainly like what we are doing with the help of cyber security. Again, like we implemented TPM 2.0 crypto processor inside in the instrument. Whenever you do communicate, it will burn the certificate. It will make sure the mutual authentication. So when I communicate, even the instrument will also like burn a certificate. It will make sure that the right person is communicating. There are types of hacking. One is like it is connected in the network. Somebody can throw the spoofing message. They try to take the communication. So that can be avoided by burning the certificate. Second, my firmware would be like always available in the website. Anybody can take and they'll try to put it in my instrument and they'll try to hack it. So tampering of the firmware, that also has been avoided. Why? Because every time it has to, even for the updating the firmware, it will do the mutual authentication first. Then only it will accept the firmware upgradation also. Likewise, whatever the ways where you can able to hack the instrument, that has been discarded. And these are the softwares like we are using. One is Test Universe and CMC Shift and Relay Sim Test. And as I told, like we will be having 3 ways of communicating, like Ethernet and your USB as well as wireless. And USB we made it little bit smart, because we don't want to like go with the old like printer port USB port. Now like we had implemented USB-C port, because that is become a universal. You can take USB-C port, just communicate. And added advantage is that whenever you communicate, it will also like charge your laptop or your mobile. It will also act like a charger.
How many watts?
How many watts? 50 or 60, right? 50. USB-C port charger. 60 watts something.
60 watts?
40 I think. 50 or 40, yeah. It's a PD actually. Automatically it will also, you can charge it.
Okay, maximum
40, continuous.
40,
40, yeah.
40 watts.
Yeah, 40 or 50. That's it. Yeah, and most importantly, like, everybody known that, like we can have a testing for, relay test kit and all. But now the idea is that we want to make this relay test kit as a multifunctional instrument. The same instrument, you can able to do all types of relay testing. Merging unit testing is possible. Primary injection is possible. Now we are just moving forward one step ahead actually. You can able to do CT testing also. So if you know Omicron, like we have a product called CT analyzer, that is a dedicated CT testing instrument. That concept has been implemented here. So what are the tests you perform in CT? Ratio, polarity, winding resistance 25 degree, 75 degree, knee point voltage, it will give you all the results. So which means one instrument can perform multiple things. And another important thing when it comes to 61850, I told you that there are some new features that has been implemented with respect to 61850. Now the world is moving towards the next phase. We expecting that everybody will remove PLC and they'll go for routable goose, R goose. So R goose has been implemented here. And now it can able to measure the sample values. And even like future is going towards the other way, routable sample values. That also has been implemented. Which means like after 5 years or 10 years, if anybody comes for that particular feature, which is readily available now.
Okay.
Yeah.
Private utilities are there.
Okay.
Taking now. We do it to station to station communication.
Because that is slowly like becoming a mandatory aspect. Because how long you will be using the same PLC and wave trap? One point of time, right? It is also maintenance cost and lot of issues were there when it comes to like maintaining the carrier signals and everything. So that's what like there are some private utilities, they already changed. They implemented routable goose so that they feel like it is secured. It is secured first, and second is fast. So that's the reason we also like implemented that feature, routable goose and everything. And another important thing that the same relay test kit will also like act like a circuit breaker timing test. That is also you can able to do it for certain level. The same instrument, right, which you can able to do CT testing, breaker, and breaker you can able to measure coil current, auxiliary contacts, everything you can able to measure it. Yeah. Overall, that's what like when it comes to CMC 500, it's safe to use. I'm sure like when you start use the primary applications, you will understand about the safety things. And when I spoke about human safety and machine safety, that has been implemented, and all the indications. Because what we heard from the customer, even due to emergency, they'll take the connection from DG set and all. By chance, right, anything fluctuate, we'll give you indication and we'll isolate the instrument. We want to safeguard ourselves, so that also has been available. So all the features has been implemented based on the feature wish, so that is possible. Manish, you want to carry forward? I'll take it.
Okay. So you have any question regarding the secondary part of the testing, because we have some solution I wanted to show you in the primary part of the testing, like transformer, breaker, CT, VT. Okay. Okay, so no question. So maybe as a utility, I think I think Yogesh also commented on the same topic that the time is equal to money for utility, right? So how much time you are spending on the testing time, shutdown time, how much you are spending for testing. If you have something that you can reduce it, definitely that will be really helpful. So that is why the topic I kept it here, like how to optimize the substation asset testings. And what is optimization? If I give you just a theory, is that an act or process or methodology, using that you can fully perfectly do your work, function or by the effective manner. And time optimization is something, time optimization is a form of time management where you can divide your time for making your work by most efficient manner, right? So that is why we have come up with the several devices. Maybe I'll skip this slide. Yeah, this one also. Okay. So before that, how many of you are into the testing team? Mainly the transformer, breaker, CTPT testing team. Are you, any one of you are from that? Okay. So just I want to take an idea like how much time you exactly take for a transformer testing, right? And which are the tests? These are the tests, for example, for transformer like TTR, static and dynamic winding resistance, no load test, short circuit, FRSL, transformer demagnetization, and then capacitance. Full 1 day, right? So this is the as I commented, for the transformer full 1 day. Maybe for instrument transformer, like ratio, phase shift, burden, magnetization, lot of things, class assessment, residual magnetism. Somehow similarly, I think we have an idea that is it takes around 4 hours somewhere around. If you are doing a conventional way of testing, like primary injection, you are doing it and then measuring from the secondary. Similar way, circuit breaker. So circuit breaker is also a main part of our substation. So like testing timing, static contact resistance, dynamic contact resistance, coil and motor current analysis, under voltage test and travel measurement. So roughly it also takes around 4 to 5 hours because for multiple tests you have to do with the rewiring between the tests. So this is an idea. So as I commented, for transformer 1 day, CTPT somewhere around 4 hours, and breaker also 4 hours. So we do have a solution where, before going into that solution, so I'll give you the background how it takes full day. So for example, conventional test kit you are having, where first you have to prepare, isolate the asset. So for example, first you have to isolate the transformer from live part so that you can do the connections and everything. Then you will connect your test kit. If you require high effort and time requirement, then you will start performing the test. So test 1. So if I take an example, test 1 is the ratio test, right? So you perform the ratio test, and between the ratio test also, you may have to change the connection between the phases R2, Y2, B. There is a need that you have to change the connection. Then test 2. For test 2 again you have to rewire. For example, you are going to do the winding resistance test. So again for winding resistance you have to rewire. Then you have to perform the test maybe for winding resistance again from R phase to Y phase to B phase. You have to change. Then again rewire. Again, depending on how many number of tests you are doing it. Then at the end, once test is completed, you can remove the wiring. Again reconnect, and this is the, after doing all the tests, you have to collect all the results from all the tests, and then you can process the data for generating a report. Okay. Overcurrent is coming.
YouTube link கிடைக்குமா?
KSEB Engineers Association.
அதில் காலையில் ரெக்கார்ட் ஆனதெல்லாம் இருக்குமா? காலையில்
இதில் இருக்கும்.
இதில் எல்லாம் யூடியூப்ல இருக்கு. ஃபுல்
எப்போ வேணாலும் அது லைவ் செக்ஷன்லேயே போய் பார்க்கணும் நீங்கள்.
இதுதானே சார்? இதுதானே?
ஆமாம். அந்த பேஜில் லைவ் செக்ஷன் இருக்குது, வீடியோஸ் ஷார்ட்ஸ் லைவ் இருக்குது. அந்த லைவ் செக்ஷனில் எப்போ
அப்போ இன்னைக்கு லைவ் ஆனது நாளைக்கு வரும்?
எப்போ வேணாலும் இன்றைக்கி தான் வரும். அது
இன்னைக்கு
ஆல்ரெடி இருக்குது, பின்னாடி போய் பார்க்கலாம். இல்லைன்னா நாளைக்கு எல்லாம் அங்கே தான் இருக்கும். வீடியோஸில் லைவ் இந்த செக்ஷன் இருக்குது.
லைவ்
அதில் இருக்கும். Day 1, Day 2, Day 3.
இன்னைக்கு Day 3 அல்ல?
ஆமாம்.
Piyush, a 9th standard student from Wales Global School, Chennai. I'm thrilled to be here. I'm grateful to the KSEB, Engineers Association, IEEE, IA, and PELS chapter Kerala for giving me the opportunity to participate in the Ideathon competition. Today I will be discussing on power system protection, electric testing technologies, and latest advancements in electrical equipment. Artificial intelligence and machine learning system. AI and ML can predict and prevent power system failures, improving overall grid resilience. Electric testing technologies ensure the safety and performance of electric equipment. Latest trends include there are multiple modern protection relays such as numerical relay uses digital processing to provide more precise measurement and advanced functionality. The second is adaptive relaying. Allows the relay to automatically adjust its settings based on real-time conditions, improving response to changing network conditions. The third is IEC 61850 standard. The standard enables interoperability between different vendors' protection devices, allowing for more advanced monitoring and control capabilities. The model protection relay, relays use digital processing to provide more precise measurements and advanced functionality compared to older electromechanical relays. The performance impact, the use of modern protection relays can result in up to a 30% reduction in fault clearing time, improving overall power systems and reliability and stability. The other trends are advanced installation testings, techniques like partial discharge testing and dielectric spectroscopy detect insulation defects and prevent equipment failures. The second, high voltage testing. Advanced high voltage testing equipment enables testing of high voltage equipment, ensuring reliability and safety. There are certain circuit breakers technology for our protection too. Vacuum circuit breaker. Vacuum circuit breaker uses vacuum as the arc extinguishing medium, providing reliable interruption of current with minimal maintenance requirements. Their compact design and fast operations make this ideal for medium voltage applications. The SF6 alternatives. It is a new eco-friendly alternative to SF6 gas are emerging, aiming to reduce greenhouse emissions while maintaining excellent insulative and interrupting performance. These alternatives include mixtures of gases that meet environmental regulations without compromising reliability. There are other breakers such as smart breakers. Smart circuit breakers integrate sensors and communication technology to enable real-time monitoring, diagnostics, and remote control. This connectivity helps optimize system performance and enhance the ability to quickly detect and isolate faults. Predictive maintenance. By utilizing advanced analytics and sensor data, predictive maintenance techniques for these circuit breakers can forecast potential failures, significantly reduce unplanned downtime by 25%. This proactive approach improves asset reliability and lowers maintenance costs. The testing and diagnostic overview. Performing regular testings on power systems equipment is crucial to ensure the reliability and operational safety. Scheduled diagnostics help identify potential issues before they escalate into failures, minimizing downtime and costly repairs. Then the common test, insulation resistance. It measures the resistance of insulating materials to prevent electrical leakages and short circuits. Turns ratio. It verifies the correct winding ratios into transformers to confirm proper voltages and transformers. Contact resistance assesses the resistance in electrical contacts to detect corrosion or wear that could affect the performance. The impact of these. Efficient testing and diagnostics prevent approximately 40% of equipment failures by detecting faults early. These proactive approaches enhance the overall reliability and safety of the power system, reducing unplanned outages and increases assets lifespan. And other than regular testing, we have advanced testing technologies. In that, partial discharge testing, early detection of insulation defects to prevent catastrophic failure. This technique identifies electrical discharges within insulation, allowing targeted maintenance before major breakdowns occur. Frequency response analysis. Assess transformer winding integrity by measuring changes in frequency response. It helps diagnose mechanical deformations or short circuits that may compromise the transformer's reliability. Thermography detects hotspots and connection issues that leads to overheating. Infrared imaging helps in visualizing temperatures anomalies, improving preventing maintenance and reducing time. Online monitoring provides continuous real-time data on equipment condition, enabling predictive maintenance and improving assets utilization by 15%. This reduces unexpected failures and expands the equipment life. Now, equipment innovations. Smart transformers. Voltage regulations and grid support capabilities through advancement series and communications modules. These transformers enable adaptive load management and improve the efficiency of power distribution networks by dynamically adjusting to changing grid conditions. Energy storage systems enhance grid stabilities and resistance by storing excess energy during low demand and releasing it when demand peaks. These systems support renewable energy integrations, mitigate outages, and help balance supply and demand in real time for more reliable power supply. Microgrids. Decentralized power networks that operate independently or in conjunction with the main grid. Microgrids improve the reliability and by providing localized energy sources, enabling faster restoration after outages and integration of distributed renewable energy resources. Wide area monitoring systems provide real-time grid visibilities using Phasor measurement units or the PMUs. and advanced analytics. These systems enhance situational and awareness, help detect disturbance quickly, and facilitate coordinated control actions across large interconnected power systems. There are simple case studies and examples as the California smart grid boosts reliability and efficiency by integrating smart sensors and real-time analytics to optimize power distribution and reduce outages across large urban areas. And there are many other studies and examples. Moving on. The conclusion is advancements are vital for safer, more reliable power systems. The key focus area is protection and equipment innovations. Continuous improvement ensures ongoing reliability and safe power delivery. And there are some energy sources other than generators for electricity production. Renewable energy sources, solar energy, photovoltaic panels convert sunlight into electricity. Wind energy, wind turbines convert wind kinetic energy into electricity. Hydro energy, hydroelectric power plants harness energy from moving water. Geothermal energy, heat from the earth's interior is used to produce steam driving turbines. Biomass energy, organic matter, for example wood or agriculture waste, is burned to produce electricity. There are other alternative energy sources too. Fuel cells, chemical reactions between fuels, example hydrogen and oxidants, produce energy and electricity. Nuclear energy, instead of the using in atomic bombs and other certain harmful things, we can use those nuclear reaction to produce steam, driving turbines to generate electricity. So thank you. That's all.
What do you mean by reliability?
So we can rely on it without any
So this is our last session. It is the PMA Wide Area Monitoring and Digital Twins. It is presented by Brijesh P. and Ajish, Joint Directors CDAC. So welcome to a wonderful session.
Good evening, all. Myself Brijesh. അവരോട് മുന്നോട്ട് മൈക്ക് വേണ്ടല്ലേ? A very good evening to all. Myself Brijesh. I am representing CDAC Trivandrum. And together with me, my colleague Ajish is also here. I hope we can share the some of the works we are doing in the field of synchronized phase measurement units and micro PMUs and worms, and also into its application in the field of digital twin. So I hope you are very familiar with CDAC for these slides. I'm directly going to the topic, synchronized phase measurement units. Briefly, I will give some basics and history of PMUs, and our portion is design and development of PMUs. Then what are the state of art technologies in the field of PMUs, and also some of the applications what we are doing in this area. So before going to the PMU, what is the relevance of a phase angle measurement in the power system? Starting from the fundamentals, power flow is defined by the equation that is between two lines we have product of voltage and divided by its impedance and the angle between these two voltage angles. That is a basic fundamental equation. Basically here that voltage magnitudes are normally same. Then the main thing which controls the power flow is the sign of the angle difference between the two lines. That is a basic need of measurement of phase angles. So in a AC power system, the power flow is defined by the sign of phase angle between two points. So then this angle measurement that can give you direct stress of your power system, how much it is loaded, what is the capacity, or whether you can increase the power flow, or whether it is going for a trip or something. That direct phase angle measurement can give you a stress of your power system. Then if you have different equipments which can measure the phase angles of different points or nodes, then you can definitely have a relative phase angle. That is the measure of your power flow. So the phase angle measurements, the things, it is not a new thing. This is a IEEE transaction paper from 1980. In this 1980, they tried to measure phase angle difference between 2 points, that is Septils and Monterey. They are about 800 kilometers apart. With then technologies, with then Lorentz-based GPS synchronization, Lorentz-based synchronization system, and we all know that time we have a limited communication features, that is like a low bandwidth serial communication. With that technology itself, they tried to measure the phase angle between 2 points. So that is the relevance of phase angle measurement. Power system engineers are, from starting point itself, they are trying for the phase angle measurement. Then after these types of primitive equipments, primitive price, we move to synchronized phasor measurement unit. That is basically an equipment which can measure your, which can sample your analog voltage or current and measure the phasor quantities and its frequency information with respect to a reference. That is the thing. And it is not only measuring, it can transmit a near real-time data into the PDC or phasor data concentrator or some SCADA system. That is the basic synchronized phasor measurement unit. Then it is not a new device or new concept. It is first prototype of PMU is developed in 1988 by Virginia Tech by Dr. Arun Fatke. Then first commercial unit is developed in 1992, Macrodyne. Still, our country witnessed the first commercial installation of phasor measurement units in, I think it is in 2011 or 12. Before that, we have made our first indigenous PMU also, and we went benchmarked with the first imported PMU installed at Northern Region Load Dispatch Center. So this is the history, and this is one of the primitive PMU units made. This is taken from the book of Dr. Fatke, and you can also see a small block diagram of PMU, which is published in 1993. We have our sensors, filters, and unlocked digital converters, microprocessor, and GPS synchronization and communication system. Still, in this 2025, the block diagram remains same, or the blocks remain same. But difference is how we are making the blocks or how we are building the blocks. Now we have more advanced analog to digital converters and the digital signal processors, and that is we have advanced digital technology, also fast communication technology. That's why the PMUs are coming to real picture or real power system from the labs or initial trials. So basically, what is a phasor? I think you all may be very familiar with the phasor. It's nothing but a quantity with a magnitude and a phase. I think you all will be very familiar, maybe more than me. Then actually you can see a sinusoidal waveform. Now that time domain sine wave we can represent as a frequency domain information. That is basically phasor. That is with a magnitude and angular frequency we can represent. So even the concept of phasor, it is not a new thing. Even not decades, it's more than a century old. It is first published in 1893 by Charles Stevens Porteous in its book Complex Quantities and Their Use in Electrical Engineering. So the concept of phasor is older more than a century. Then the phasor measurement units, that commercial things that comes more than four or five, maybe 3 to 4 decades before. Still, we don't have much commercial installation in our country. So, coming from phasor to synchrophasor, what is basically synchrophasor? Nothing but it is a phasor, but now we have to define a reference. That is a phasor quantity which is defined with respect to a reference. That is a synchrophasor. So, when different people are making the phasor measurement units or synchrophasors, definitely we have to work in operability mode. So it should be based on a standard. So as per IEEE standard, it is defined as if your positive peak occurs at a UTC rollover, then you can term it as a 0 degree phase angle. If your positive zero crossing is occurs at UTC rollover, you can term it as a minus 90 degree. This is a conventional representation of a phasor. Basically, this is for interoperability between different makes and all. So, if you are installing two PMUs in two sides of a node, two nodes of a bus, then what you are effectively getting is the actually phase angle measurement at a particular or single node is doesn't have much relevance. When it comes to a angle difference, that is making the point. So you can directly with the PMU, that is with a global reference, you can directly have a phase angle difference between the two nodes. So basically people are going for GPS based synchronization, which is the cheaper and easier thing we can use now. Actually, this is a observation in the New York Times after the blackout occurred in USA in 2003. At that time, they are actually installed some instruments, but they were not well monitored. The New York Times told they observed that if they were well monitored, they would have get enough time for stopping the catastrophic blackout occurred in 2003. Basically, PMUs are those devices, and PMU can provide you a somewhat early warnings. That is, even with the general visualization of PMU data, an operator can have a feel of how your power system is going. Then the first application of PMUs in power system is wide area monitoring. Then actually CNAC initiated the development of PMU in 2008 or 9 itself, and 2010 we made first indigenous PMUs, and actually that time we don't have any testing facilities in India for PMU. Even now we don't have much testing facility, and this is the basic block diagram of the PMU. Actually I told there won't be much difference from the primitive version in the case as a block level representation, but how people are realizing it, that is makes a difference. So this is the basic time synchronization. I am not going into deep. From GPS receiver we will get two signals. One is 1 PPS and another is your timing information. Both we can use for the, one is for the triggering your ADCs for the synchronization, and one is for the time tagging that you can use. And actually this is the basic, basically as per IEEE standard, they are just defined what is PMU and how you have to estimate the phasor values. They are not defined that one. And another thing is you can use different reporting rates for the PMUs. Phasor data you can communicate in different reporting rates. For 50 Hz you can go for 10, 25 or 50 or even 100 samples per second. This is the basic reporting frame. These are the basic standard IEEE 37.118 standards. That is the basic standard for PMU. And this is the basic building block diagram of PMU. Then there are different methods for phasor estimation. Either you can go for DFT based phasor estimation, or you can go for FFT based things. Then you can get even you can calculate the DHT information and all. So there are different methods. Either you can go for a recursive based DFT or normal DFT. So this is a known effect in the phasor estimation. Basically, when your grid frequency is not exactly the 50 Hz, then double harmonic content of that line frequency will be there in your estimation. So you can go for a positive sequence estimation for calculation of the frequency. Basically, one advantage of PMUs, you can get a more accurate frequency measurement from the PMUs. If you are directly going for angle, basically PMU's frequency is d theta by dt. If you are directly going for that d theta by dt, there will be noise. Then people are going for positive sequence based frequency measurements. Then this is the basic communication scheme for a PMU. This should be as per standard. Your PMU should communicate with the PDC with as per standard. You can at your sampling rate, you can define the sampling rate, or your signal processing things or algorithms you can define as your own. But the communication between the PDC or anything, that should be as per standard. This is the basic message exchange between the PMU and PDC. Basically, PDC will send a configuration request to PMU. Then PMU will send its configuration frame that will contain what are the information the PMU is communicating with the PDC. Basically, one PMU can be different with other PMUs because sometimes one PMU can send 12 voltage signals or 12 current signals. Another PMU can include much more quantities. These all defined in this configuration frame, and this is a basic data exchange between the PMU and PDC. So these are some laboratory level testing we usually do for verifying the signals. Actually, just go through the. This is the first one of our first proto unit we developed. This you can see. This is the first proto unit we developed in our lab in 2010-11, and this is actually installed in Northern Region Load Display Center, Delhi. Actually, this is from imported PME from SCA. Maybe that is the first PME imported in India. And this is our PME. Actually, for benchmark testing, we collected data from SEL PMU and our PMU. Then we made certain analysis based on some data collected from SEL PMU. That is in the year 2011. These are different data from Sree PMU and our first proto PMU and SEL PMU. And actually, with support of KSEB, we had a pilot implementation of ARM system, a scaled down implementation with 4 PMEs installed in transmission substation, and our phaser data concentrator installed in LDC, low dispatch center. And with fiber optic communication of KSEB, we communicated, and that is collected in the low dispatch center. Actually, this is the first of its kind installation with the indigenous, totally indigenous subsystems. And this is in the year 2015 and 16. Actually, this is PME from different substations. That is, one is from Arikot transmission substation, and one is from Madakatara transmission substation. So these are some pilot installation in that one deployment from a different Arikot, Madakatara, and Kaniyambeta in Kollam substation. So and then
references.
That is a GPS reference.
So RYB you will be having that.
No. A single reference. Actually, from your GPS receiver, you will get 2 signals. One is 1 pp signal. At every 1 second, you will get a pulse. Then PMU's internal clock will be synchronized with that pulse. So,
one waveform will take as a reference,
yes.
and you compare the remaining to the reference.
Yes. Basically, that reference is derived from GPS signal.
Reference is GPS.
Yes.
One signal you will take as reference.
Yeah.
Others you will compare to this.
Yes. So there are different applications. First is phase angle monitoring. Then
See that you are manufacturing
actually we are a R&D organization of Government of India. Actually we will do research and we will transfer technology to other industries. We are not a manufacturer, but we will do proto units and pilot deployments. Yeah, actually we will do research, we will do first prototypes, and even we will go to actual site and technology, we will demonstrate technology, but we are not into mass production or such.
But you also develop PDC also?
Actually PDC, basically that software part will be.
As R&D support, you give support for PDC also?
Yeah.
But in the market there are, you must be aware, there are different PDCs,
but
different PMUs.
Everything should be interoperable.
So this device, what we are seeing, this also can handle the PMU.
PMU functional.
PMU functional.
This pulse, what is the frequency with their pulses?
From GPS. At every second we will get a pulse.
1 second.
1 second. 1 hertz.
GPS signal ആണ് GPS.
GPS signal ആണ് derive ചെയ്യുന്നത് നമ്മളുടെ
അല്ല NTP സംഭവിച്ചില്ലേ?
അല്ല അതിനേക്കാളും ആക്യുറസി ഉള്ളത് GPS ആണ്. ആക്ച്വലി
അതല്ല ഒരു സെക്കൻഡിൽ മറ്റേത് പൾസ് കിട്ടും.
അതെ
NDT എന്ന് പറയുമ്പോൾ സെക്കൻഡിൽ താഴെ പോയിട്ടില്ല.
അല്ല അതല്ല ആക്യുറസി. ഇപ്പം നമ്മളിപ്പം ഇപ്പം ട്രിവാൻഡ്രത്താണെങ്കിലും ഡൽഹിയിലാണെങ്കിലും നമുക്ക് അല്ല നമുക്ക് GPS യൂസ് ചെയ്യുന്നത് GPS-ലാണെങ്കിൽ നമുക്കിപ്പോൾ ഈവൻ ട്രിവാൻഡ്രത്താണെങ്കിലും ഡൽഹിയിലാണെങ്കിലും മാക്സിമം ആ ഒരു ഷിഫ്റ്റ് എന്ന് പറയുന്നത് ഒരു വിത്തിൻ 1 microsecond ആയിരിക്കും. ആ 1 പൾസ് കിട്ടുന്നതിൻ്റെ ഷിഫ്റ്റ് നിലവിൽ ഏറ്റവും ആക്യുറേറ്റ് ആയിട്ട് നമുക്ക് അതായത് ഇപ്പം പറഞ്ഞാൽ നമുക്ക് ഈ 1 സെക്കൻഡിൽ താഴെ എപ്പോഴും പൾസ് ഇത് റെഫറൻസ് സിഗ്നൽ കിട്ടിക്കൊള്ളുന്നല്ല ഞാൻ പറയുന്നത്. അവിടെ കിട്ടുന്ന ആ പൾസും ഇവിടെ കിട്ടുന്ന പൾസും തമ്മിലുള്ള ഡിഫറൻസ് മാക്സിമം വിത്തിൻ 1 microsecond.
അനലോഗ് അല്ലേ സാധനം?
അതെ അതെ.
അപ്പൊ അനലോഗ് ഇല്ലാത്ത കേസിലോ ചില ഇതിന് TPS ഔട്ട്പുട്ട് കാണാത്ത കേസിൽ നെറ്റ്വർക്കിൽ മാത്രം വർക്ക് ചെയ്യുന്നത്?
അല്ല നെറ്റ്വർക്ക് നമുക്ക് സിഗ്നലൈസ് ചെയ്യാം, നമുക്ക് എന്ത് വേണമെങ്കിലും യൂസ് ചെയ്യാം. പക്ഷേ GPS ആയിരിക്കും നിലവിൽ ബെറ്റർ.
GPS-ന് തന്നെ PTP ഔട്ട്പുട്ട് ഒക്കെ വരുന്നുണ്ട്. PTP ഔട്ട്പുട്ട് വെച്ചിട്ട് സിങ്ക് ആവും. പ്രസിഷൻ ടൈം പ്രോട്ടോകോൾ
ആക്ച്വലി ഞാനിപ്പോൾ ചെയ്തിരിക്കുന്നത്
TPS ഇപ്പം അങ്ങനെ യൂസ് ചെയ്യാറില്ല.
ഇപ്പം ഈ റിസീവറിൽ അങ്ങനെ കാണാറില്ല. അല്ല നമുക്ക് എന്താ ഒരു ഗ്ലോബൽ എന്ത് റെഫറൻസ് ആണെങ്കിലും സിങ്ക് ചെയ്യാൻ പറ്റും. ഇതിൽ ഞങ്ങളൊരു ജസ്റ്റ് ആക്ച്വലി ഡിഫറെൻറ്റ് 1 PPS ഉള്ള ആക്യുറസി നാനോ സെക്കൻഡ്സിലാണ്. അപ്പോൾ അതുകൊണ്ട് യൂസ് ചെയ്യുന്നത് നമുക്ക് ബെറ്ററായി കിട്ടുന്ന എന്ത് റെഫറൻസും യൂസ് ചെയ്യാൻ പറ്റും. ഈവൻ നമുക്ക് ഇങ്ങനെ ഒരു സിഗ്നലൈസേഷൻ വേണ്ടാത്തടത്ത് നമുക്ക് നെറ്റ്വർക്ക് ടൈം യൂസ് ചെയ്യാം.
അല്ലെങ്കിൽ ഒരു ഗ്രിഡ് ഡിസ്റ്റർബൻസ് ഉണ്ടായാലേ ഒരു ഗ്രിഡ് ഡിസ്റ്റർബൻസ് ഉണ്ടായി കഴിഞ്ഞാൽ നമുക്കിപ്പം പല PMUs എന്നുള്ള ഈ ഡേറ്റ എടുത്തിട്ട് നമുക്ക് ഡിസ്റ്റർബൻസ് അനലൈസ് ചെയ്യണമെന്ന് വെച്ചാൽ മില്ലി സെക്കൻഡ് ഡിഫറൻസ് ആയിരിക്കും ഈ ഇതാണ് റീസർ ചേഞ്ചിൽ വരുന്നത് മില്ലി സെക്കൻഡ്സിനായിരിക്കും ഒരു ഡിസ്റ്റർബൻസ് വരുന്നത്. അപ്പോൾ അതെങ്ങനെയാണ് നമ്മൾ ഈ സിഗ്നൽ സിഗ്നൽ വെച്ച് നമ്മൾ അനലൈസ് ചെയ്യുന്നത്?
അല്ല PPS സിഗ്നൽ വെച്ചിട്ടല്ല, നമ്മൾ അയക്കുന്ന ഡാറ്റ നമ്മൾ ഇപ്പം നമ്മളുടെ PMU-ന്ന് ഇതിലേക്ക് അയക്കുന്ന ഡാറ്റ ഒരു PDC-യിലേക്ക് അല്ലെങ്കിൽ സ്കാനിലേക്ക് അയക്കുന്ന ഡാറ്റ എന്ന് പറയുന്നത് ഒരു ടൈം ടാഗിൻ്റെ ഡാറ്റ ആയിരിക്കും. അതിൽ ഇന്ന ടൈം സെക്കൻഡ് മില്ലി സെക്കൻഡ് മൈക്രോ സെക്കൻഡ്
എല്ലാം ഉണ്ട്.
മറ്റേ നമ്മുടെ SOC സെക്കൻഡ് ഓഫ് സെഞ്ചുറി വെച്ചിട്ടുള്ള ഡാറ്റ ആയിരിക്കും നമ്മൾ അയക്കുന്നത്. അത് വെച്ചിട്ടാണ് ഇത് ഈ 1 PPS എന്ന് പറയുന്നത് സിഗ്നലൈസേഷന് വേണ്ടിയിട്ടാണ്.
Now you do any analysis part. Suppose if PMU is installed with the PDCs, if any utility, CDAC is conducting any analysis portion for the given period of time, or what is your role for the existing installed PMUs in the utilities?
Actually, we are not commercially we are not doing analyze that utilities, but now we are trying to develop applications like a digital twin center with this sensor data.
We are taking the analysis for our own purpose,
not for some
research purpose.
Only for the research. So actually this is a setup. Actually this type of setup we can well utilize. Basically that is a real-time simulator. We are integrating real-time simulator with PMU, and you can simulate your power system in the real-time simulator, and that you can analyze. That Ajish will give you more details on that. This is a setup we made in 2016 in CPRI, but now we are doing this with our own simulator that Ajish can. These are some of the faults we created in real-time simulator, and
this is captured in PDCs.
Yes, basically this we generated with real-time simulator and that real-time simulator captured this data is given back to
this data, whatever you have shown, this is extract of PMU or PDC's data.
PMU. That is PMU data given to PDC from PDC. That PMU you can use
output of PMU
output
against the RTDS.
Yes. Even you can use the PMU connection tester utility for data saving and even the RTDS is doing the same thing. They are using that application, PMU connection testing application. But now we have our own real-time simulator for this.
Your own RTDS system.
Not RTDS system, our own simulator.
Simulator to test PMUs.
Yeah, basically indigenously Sree we made that simulator.
And you are authorized. You are any authorized laboratories kind of thing. Suppose if I want to test my PMU, I can authorize.
But
like CPRI.
No. CDAC is not a testing agency in that case. For our own evaluation, we are using our own real-time.
Some of the norms are there. Testing should be in test lab or
That's what. Suppose I am a OEM, so I want to. You don't know nowadays there are a lot of standards are coming out today. So we want to get it certified. Yes. There are a lot of test agencies also.
Yeah, actually what we are doing is in everything, that is these PMUs. Basically we are working in power points. These converters, everything we will make our own tests, bench or test arrangements, and after that only we will go for some certification. Basically,
because after this 2011 event, you also remember blackout of Northern Grid.
Yeah.
So Power Grid is issued all utilities to have the critical feeders PMUs. All the OEMs that time PMU was in the initial stage. So later they got developed and many even you might have heard this Kalki Tech also. They are cheapest. They are
I know.
Installed their own PMUs and PDCs. As a Siemens, we also have
PMUs. Actually, I think they use from National Instrument Center, but PDC they have.
PDC they have.
Kalki Tech.
So now, recently there is a guideline from CEA for all the utilities to use PMUs for the 220 kV level substations.
Yeah. Actually, up to this time, what I explained is basically PMUs which is installed in transmission subsystems. Now, the PMUs are application of PMUs are into distribution also. Basic scheme, everything remains same, but when it comes to a distribution system, there are some differences. Basically, first difference is money flow in a distribution system is very less compared to a transmission system. So, you need to make PMU with less cost basically. But when comparing to a transmission system, that impedance, that inductance or something between these two distribution lines are very less, and your phase angle difference between two nodes are very less compared to a transmission system in a distribution system. So you have to make low cost PMUs with more accuracy than a transmission type of PMU. But now we are working into that distribution PMUs also. This is one of the distribution PMU we made in our lab. Actually, we have a project jointly with the Kerala State Electricity Board, that is Smart Power Quality Center. This in one of the actually that is a combination of 6 projects, and one of the project is Intelligent Sensor Network for Distribution System Monitoring and Control. As part of that project, we developed this distribution PMU, and we installed in 1 or 2 stations, Again, basically in this distribution PMU, you have the phasor measurement, then frequency and rate of change of frequency information. That is basic PMU measurements. Additionally, we are having active and reactive power, power factor, harmonics. These are measurements we are having. Even required, we can have additional measurement also. I can just show.
What is the significance mainly on distribution network of PMUs? Because transmission is okay, we understand.
Yeah.
At distribution level, what they do with this data?
I think in next presentation, Ajish can better handle that. Actually, this is a real-time data from all two installations in Kerala. One is
The live data?
Yeah.
that is live data. For you. Actually, one is from one Milma dairy plant is there in Toronto. This data is from there. We have the phaser information. Actually, these are phase angle information, and we have the current voltage and current PHDs. Then frequency measurement, then power factor, active and reactive, current. These are live data from access system. Actually, you can also show. Basically, this general hardware we made for transformer monitoring also in our Technopark substation. Even you can add environment parameters to this system. So these are configurable. Additional to the PMU data, or if you are specific with some other data, we can also include that also.
That sensor should also be integrated.
Sensor should be. Here you can see very high PHD values. It is in IT park basically. That's it. That Milma, it is about 5 to 6. So it is an IT park. Additional to this monitoring features, we can also include some control functionalities. As part of this project, what we done is we integrated this PMU with a StatCom, and that StatCom also installed in the Milma Ambaltara diary. Previously, where I shown the PMU data, and the PMU is based on the PHD data. PMUs remotely control the StatCom for maintaining this harmonics or power factor. That control functionality also we can integrate to the system. Actually, we have the complete flexibility in this case. So this is some StatCom control that you can.
StatCom is there in that Technopark.
Actually, as part of this Smart Power Quality Center project, we installed one StatCom in Milma direct plant.
KSEB themselves have made one StatCom for the Technopark, right?
think Technopark, I'm not sure about that because
They had some stuff.
actually Technopark in 5 or 6 years before we had some Stato installation. CDAC with the CPRI support.
That is still there, right?
Actually, that is not completely functional. They're shifting or something. That is piloted with testing only.
First time the STATCOM was produced and then installed at the
that is 2 MBA STATCOM. Then this thing I already explained. Then there are some applications in distribution PME that thing Ajish can better explain, like the event detection. Then definitely fault identification we can do with PME data. Then even when it is when the more renewable energy and the EV systems are integrated into our system, that distribution grid is more unpredictable. In that case, even with PME data, you can look for mass load identification and all. So these are some reference for microwave applications. So even the architecture of PME is you can, if any, we also have merging unit. We also have merging unit. That is now you can actually sample and complete samples you can send to some higher level, and then you can do PME applications things. Also even in this micro PMU, what you can do is you can log some particular data based on the events, event based data logging. It is not necessary to log all complete information, and you can, based on the event based, if some events are detected, you can log that data and you can communicate that for post-mortem analysis. So that much of flexibility is there. We have more powerful processors are now available, and the communication medium well. So from my side, thank you everyone for even in this very late time. Then Ajish will give you introduction about this.
It won't take much time. It's a concept.
Shall we start? Yes. So digital twin. Actually, this is a wide concept, and it actually requires a lot of time to complete the information regarding digital twin in power system. The definition of a digital twin is a virtual replica of a physical product or process or any system. Here you can see that if we have a motor, a physical system, and if we have a digital representation of exact digital representation of the physical system, we can do a lot of things with that one. So that is actually the meaning of digital twin. It's a virtual representation of the original physical system. Suppose if I created a twin of mine in a digital computer, exactly mimicking my nature, my feelings, everything. And of course we know that it is impervious to injury, pain or any hard feelings. So if I want to know what happened if I jump from the top of this building to the ground, and I created a virtual world there, and before doing that one, how much, at what percentage of injury I can have if I do that jumping from the top of this building, I can perform that with my digital twin or digital representation of my exact human, and then I can perform in a non-destructive way, so that I am not, anyway I don't have any pain or anything, but I will understand what exactly happened if I jump from the top of this building, if I alive, or if my leg is broken or my hand is broken, which part of my body is having serious injury, everything I can predict before if I do the actual operation. I am not going to do that one anyway. So what I am trying to tell is, if I have a digital twin of a physical system, we can exactly take make decisions of yourself with a lot more accuracy, a lot more certainty of the outcome. That is the use of digital twin actually. The digital twin actually begins in 2002 by Professor Dr. Michael Greaves at University of Michigan, and he introduced the concept of mirrored space model for the product life management, and later this is adopted by NASA in 2010, and of course Dr. Michael Greaves then worked in NASA for making the word digital twin is actually given by NASA in 2010, and Professor Dr. Michael Greaves worked in NASA for making the digital twin of some of their aircraft, and which is a virtual counterpart of the physical aircraft, and they used this digital twin technology, started the digital twin technology in their Orion mission, space mission. Then in 2012 to 2015, this was given to academics and industries for making more accurate models of the system, digital twin model, and then it was adopted by GE, Siemens and a lot of other companies. And in 2015, early 2015, IoT based sensor networks are also integrated into the system, so that a complete closed loop environment of the digital twin was started with that one. If you see the history of digital twin technology, it is actually NASA actually began with their first moon mission, Apollo mission, but there they used the analog counterpart of the spacecraft models. In 2016 to 18, the commercialization of the technology actually started, and GE now their Predix platform, it's a cloud-based platform. We can use it for creating our own digital twins, and a lot of other companies are providing their cloud-based technologies for creating the digital twin. And in 2018 to 2019, the power engineers actually started using the digital twin technology in healthcare, digital twins for organs, patients and medical devices actually started. In healthcare, actually earlier we are testing the medicines on rats, monkeys, other species. Now they started in digital twin of the organs or the human body or the DNA, and on that DNA they are started testing the mathematical. It is actually a mathematical, digital twin is actually a mathematical model, and they started modeling the chemical process, everything by mathematics, and they are started testing the started testing the medicines, and they are started mimicking the behavior of heart, lungs. It's basically they are started representing the hearts, lungs with the mathematical representation, and of course they started using, because these are some of the things are, it is very difficult to represent in mathematical format. They started using AI and ML to model the digital model the physical systems. And 2019 at present, we are now using the digital twin. We started using in different areas, in logistics, agriculture, defense, retail and finance, and it is also started as a service, the digital twin. Now there are a lot of companies which provides a digital twin as a service to the industries. Types of digital twin. This is the basic type of a digital twin, which represents a single part of or component, example a valve or sensor, which focus only on the local behavior of the parts of the big system, example a gear, and which the digital twin can predict the wear and tear of the failure rate of future failure chances of the original gear. This type of digital twin are called part twin or component twin. Then we have asset twin. With the part twin, we are actually making the complete set of a complete model of a physical system. Example, an engine or a, for example, an engine or a transformer with a transformer oil winding, twin model of the transformer oil winding and the fins. With that, we can create an asset, that is our transformer, which is for actually used for predictive maintenance and life cycle analysis. Then comes the unit twin, a group of assets working together. Example, we can say that a substation is a, if I create a substation twin with transformers, transmission line, loads, relays, twin model of relays, everything, then I can say that it is a system or a unit twin. Then we have a process twin. For example, the manufacturing process in an industry, we can model it as a digital twin, and we can do some prediction, or we can test different scenarios. If I change one process cycle, what will happen to the complete process, so that I can predict most of the events which are going to happen in the process. And is anybody uses digital twin till now? Anyone in the room? Actually, we are using Google Map is a digital twin. So with Google Map, we can see what happened if I take this road. What will be the traffic? By at what time I will reach there? If I go this way, what will happen in future? What will happen in that way? I can see some red lines, so that most of the time I can take a decision, so that not go with that line, go with take some other deviation. So that is a very good example of a process twin, which is a Google Map, which actually collects real-time data from the field, from the original physical system. That is, most of the people are using mobile phones, and they are using their Google Map application itself. They are taking that real-time data and predicting they are modeling the traffic system, and they are predicting the traffic and estimated time of arrival, and the cost of fuel travel if I take this way. So based on that, the Google Map is giving a lot more information for that, so that the user can take a faithful decision. Coming to our engineering real application, I am coming to the power system. Suppose I have a pressure pump, and inside that pressure pump I have motor, some gear pump, pressure sensors, some solenoid valves, and one reservoir. If I model that in a, let us say, in a computer as a program, if I model everything inside that pressure pump in a mathematical model, and somehow we will see how we can supply the input to that one, and I am giving the exact input which I am going to give the original pressure pump in the same way as to the in the same sense to the digital tin or the mathematical model of that system. Then we can see that since I modeled exactly the same replica of the physical system, the pressure pump. Fortunately, in engineering we have mathematics to model these things. So if I give the exact input which is going exactly to the physical system, then the digital tin also behaves like the original system. That is the concept behind digital twin. So that in parallel to the original system, a mathematical or a virtual model of the original system is working, and which will give you the exact output of the, if I model exactly the same way as that of the physical system, it will give exact output of the original system. So what is the advantage of this one? Suppose I don't have any information regarding the internals of the pressure pump. What is the temperature inside that gear, and what is the status of that solenoid valve? Everything I can predict I can see from the digital tin without opening or without measuring. That is the one advantage, without measuring the original plant. So I can verify, so that the digital tin actually verifies the simulated and measured pressure, whether they are matching. Accordingly, it will automatically adjust its parameters to exactly mimic the original pressure pump. So what is the advantage is that I can determine all the internal state or internal variables, internal pressure, temperature, the status of different valves. I can determine all the states of the system. So this is the advantage of digital twin. Now this is the digital twin representation of a transformer. Of course, we cannot directly give the transformer incoming voltage to the mathematical model that is maybe running in a computer. So we need fortunately we have data acquisitions from the transformer. So sensor data and some historical data that can give to the simulation model, the mathematical model, exact mathematical model of the transformer. Of course, some of the events it is very difficult to model in mathematics. For example, the corrosion rate of the corrosion and color change of the oil inside the transformer. In that case, we can use some machine learning techniques so that the historical data we can feed to the machine AI model, so that it will finally it will come to exactly mimic the nature of the transformer oil. Then we can say that we can have a digital twin of the transformer. So in the context of power system, it is actually the virtual representation of the physical power system. Now we have seen that we need to give some inputs to the twin. So from where we will get the input to the twin? Fortunately, we have a lot of data collections and data sensors inside the power system currently. PMU, smart meters, SCADA. We have a lot of sensors and a lot of data we have. So we can have these data sources from the original power plant, and we can feed that to the mathematical model, so that the mathematical model continuously, that means it will update in real time. Actually speaking, it is faster than real time. In digital twin case, we need a faster than real time execution of the system. The architecture of a digital twin in a power system is actually a layered architecture, where we have the physical, first we have the physical power system, which consists of the our assets like a transformer, transmission line, SCADA, IoT devices, smart meters, and a lot of sensors, PMUs, everything. And then we have a connection layer which connects this is the important layer which connects the virtual representation of the power system with the actual plant. So that in power system we have different communication standard, IEC 61850, Modbus, DLMS. So we can use any the sensor data. The twin must be capable of taking any data from the power system, and so that the voltage, current, the state of the breakers, temperature, weather condition, everything will feed to the virtual model of this power system, so that it exactly mimic the original power system. Once we have this thing, then we will give this to the data layer, where the data layer is doing some A and ML operation, so that which will validate the truthfulness of the data, and we can do some big data analysis on the huge data which is coming. If we know that if we don't have the historical data for doing some A and ML operation, that we can tell to the tin to generate some historical data and simulate some conditions in a faster rate, so that you give that data to the A and ML to perform the application, and we no need to wait for the from the original power system, we no need to wait for the data to be generated for a long time. So then we can give this to the service layer, so that they can have some economics aspects, and the operator can take some decisions based on the total data collected from the twin and the physical system. Once the twin will, then there is a feedback to the service layer to the twin, so that the twin will adjust its parameter according to the because as far as the twin is concerned, it don't know what is the for example, if we take a transmission line, it knows that there is a transmission line, but it don't know what is the parameters of the transmission line. So the twin, the responsibility of the twin is to predict the parameters of the transmission line. What is the RL values, RL or the LC values of the transmission line, because it requires a mathematical model. So it will predict the mathematical model based on the data collected, so some of the feedbacks from the top layer, and it will iterate and update its twin nature. So you see, the virtual layer, this is actually the heart of a digital twin. In power system, most of the physical systems we can represent it as a mathematical thing, and it should require a high performance computer platform. Usually the digital twin in power systems are realized using real-time simulator. The component modeling is actually the core part in the modeling of the digital twin technology. It should have the generators, transformers, substation, transmission line, all the assets model. We need to model all the assets in the digital our actual power system, and which should run in real time or faster than real time. So coming to the component modeling, some of the approaches, normally if we have only one frequency component, we are interested only in 50 Hz, then we can use the quasi-sinusoidal or phasor model, which is mathematically very simple. But if we want to exactly model the equation, the system, we need to go for the original or the EMT equation, which is called the electromagnetic transient equations. The EMT simulations actually takes, modeling of the systems actually takes more time, computational time, than the quasi-sinusoidal model. But as far as now the modern power system is concerned, we know that there is not only one frequency, 50 Hz. We are not only interested in 50 Hz components. There are power electronics which injects harmonics. So, which also demands for forces the pupil to model EMT simulations. Yeah, the data is collected from various sources: sensors, SCADA, smart meters, PMUs, and weather forecast, market data. And of course, to the twin, we need to send the huge amount of data. Sending this huge amount of data in a normal channel is very difficult, and we need to use some compressive sensing samplings. That means we need to compress the data so that it has to, like MP3. We know that earlier we have CDs, wave file format, which take a huge amount of memory. Then we compress the data so that MP3 comes. Like that, we need to do some compression in the total data. Then only we are able to transfer the whole data in a real-time manner. Then the purity of the data, whether I can trust the data, that is actually estimated through state estimation. And this state estimation not only do the purity test, but also finds out the parameters, the transformer tappings, temperature, and what is the transmission line resistance, load values, current values of the load, everything by the state estimation algorithm. So all these are done through a real-time simulator. And CDAC with IEEE developed a real-time digital simulator, so which is having 40 processors inside the simulator, and for data acquisition time of 1 microsecond is possible with that one. And that time step is right now we achieved up to 200 nanosecond time step. It is not 10 microsecond, it is 200 nanosecond time step with this real-time simulator. And we are now designing, modeling the digital twin of a substation, KSEB substation, which is a Muttatara substation. Before that, we are trying a pilot small test project at our Technopark campus. This is the basic architecture. We have the real-time simulator, and we are collecting the data from the substation. And then multiple instances of the substation is running inside the simulator, which one will do the dynamic state estimation, which exactly found out the state, the voltage and currents at the different nodes, which are some nodes we don't have sensors, and it will predict that what is the voltage and current at that nodes. And parameter tuning, it will do the find out the parameters of the system. And some instant 3 will run faster than real time. Suppose if one relay is tripped, what is going to happen in next event? So that it will simulate different conditions in a faster than real time nature, and it will alert the operator. So this is going to happen. So that is the use of digital twin in a power system. So this is we can do some what if conditions in the existing power system without disturbing. If I am going to switch on one load, what will happen? And if I am going to inject some solar power, if we are going to turn on some solar power plant, what will happen in the original power system? These type of things we can do with the digital twin. Predictive maintenance is other one, and optimization and control. And finally, the training and decision support for the operators and engineers in the exact power system. So these are with this I am going to conclude my presentation. Thanks for your patience.
We are actually looking forward once it is complete.
Yes. So.
So all our sessions has come to an end, and the last session was very interesting. We got some insights into the working of the PMU. So thanks again for SEDAC for such a wonderful session. Okay, we will looking forward for your continuous support in future sessions and programs. Thank you very much.